Hello there, and welcome to Science for Sleep, where curiosity gets cozy and the universe slows down just enough for us to wander through it together. Tonight we're travelling to a place so extreme, so impossibly close to its own star, that the planet itself is beginning to come apart. Not from an explosion, not from an asteroid, not even from some dramatic collision worthy of a summer blockbuster trailer voice. No. This world is being slowly stretched, overheated, and consumed by the very star it orbits. Its name is WASP-12b, which admittedly sounds less like a doomed alien world, and more like a password someone created in a hurry. But behind the awkward name lies one of the strangest planets astronomers have ever discovered. A giant world larger than Jupiter, orbiting so close to its star that its skies glow with unbearable heat, while gravity itself pulls the planet apart like soft taffy. And somewhere out there tonight, while Earth quietly turns beneath your window in your room, slowly settles into darkness, this distant planet continues spiralling toward destruction, not quickly, not all at once, but steadily, patiently. A slow-motion cosmic disaster unfolding over millions of years. There's something strangely unsettling about that, isn't there? We tend to think of planets as stable things, reliable things, huge stone or gas spheres calmly circling stars for billions of years while life either appears on them or doesn't. Even the dangerous worlds in our imagination usually explode dramatically. But WASP-12b is different. This planet is not meeting a sudden end. It is being unravelled little by little, hour by hour, orbit by orbit, which makes tonight's journey oddly personal in a way. Because if there's one thing humans are deeply uncomfortable with, it's slow endings, the dripping faucet, the battery percentage sliding downward. The suspicious sound your car has been making for 3 months that you keep pretending will resolve itself emotionally. Slow processes make us uneasy because they remind us that the universe rarely hurries. Stars form slowly, galaxies drift slowly, mountains rise slowly, and planets, it turns out, can also die slowly. Before we drift further into this overheated corner of the cosmos, though, I'd love to ask you something simple. Where are you listening from tonight? Is it late evening where you are? Early morning? Are you curled beneath blankets while rain taps softly outside, or sitting awake in the quiet glow of a lamp while the rest of the house has already fallen asleep? It always amazes me that these journeys happen across so many different places at once. Somewhere, somebody is listening from a crowded city apartment while traffic hums faintly outside. Somewhere else, another listener is tucked away in a small town where the night is almost completely silent, except for distant wind or creaking floorboards, and somehow all of us, scattered across continents and time zones, arrive together beside a planet over 1,400 light-years away. Space is very good at making Earth feel both enormous and very small at the same time. Now, if you find these slow little expeditions relaxing or interesting, or simply a pleasant way to unwind after a long day, I'd be ever so grateful if you liked the video and maybe subscribed as well. It helps this calm little corner of science drift toward more people who might need a softer landing place for the evening, and hopefully tonight's subject won't keep you too awake, although I will admit giant melting planets do have a certain talent for lingering in the imagination. So, settle in for a while, let your thoughts loosen their grip on the day behind you. There's no rush here. The universe has been doing this for nearly 14 billion years. We can take our time. To begin understanding WASP-12b, it helps to start with something familiar. Our own solar system feels relatively calm. Mercury is hot, certainly. Neptune is windy enough to make Earth hurricanes look rather embarrassed. Saturn has enough moons to start a respectable collection. But overall, the planets here behave themselves. They follow stable orbits. They keep respectful distances from the Sun. Even Jupiter, enormous as it is, circles comfortably far away in the cold outer regions. Earth, meanwhile, sits at a distance that allows oceans to exist as liquid water. Not frozen solid, not boiled into steam, just balanced enough for clouds, rivers, forests, and tired humans reheating tea at midnight. Astronomers call this sort of orbital region the habitable zone, though that phrase can sound a bit grander than reality. It simply means conditions are not immediately catastrophic. But not every planetary system turns out so politely arranged. Once astronomers began discovering planets around other stars in the 1990s, they quickly realized the universe has absolutely no obligation to organize itself according to our expectations. Some systems contained giant planets orbiting unbelievably close to their stars. Others had worlds moving on bizarre elongated paths. Some planets seemed denser than iron. Others appeared puffed up like overheated balloons. And among these strange discoveries, certain planets stood out for being especially reckless. These became known as hot Jupiters. The name sounds almost cheerful, like a weather forecast for Jupiter during an unfortunate summer vacation. But hot Jupiters are genuinely extreme objects. They are massive gas giants similar in size to Jupiter, except instead of orbiting far away in icy darkness, they circle terrifyingly close to their stars. Imagine taking Jupiter and dragging it inward until its year lasts only a few Earth days. Actually, in the case of WASP-12b, less than a single Earth day. One complete orbit takes about 26 hours. That means while you're sleeping tonight, this planet will almost complete an entire year. By tomorrow evening, it will already be racing through another one, and because it orbits so close to its star, the conditions there are difficult to overstate. Temperatures climb above 2,500 degrees Celsius, hot enough to melt many metals, hot enough that molecules themselves begin behaving strangely, hot enough that the planet glows faintly red from heat, alone, like an ember in a fireplace. At those temperatures there are no calm cloud layers drifting gently through blue skies, no oceans, no storms like the ones we know on Earth. The atmosphere itself becomes violent beyond ordinary intuition. Yet even that is not the strangest part. The truly unsettling detail is that the star's gravity is actively tearing the planet apart, not metaphorically, literally. Gravity is stretching WASP-12b into an egg-like shape. The side facing the star experiences such intense gravitational pull that material from the planet is beginning to escape entirely. Gas streams outward into space, pulled away like water spilling from an overfilled cup. The star is feeding on its own planet, quietly, continuously, and astronomers can actually see evidence of this happening. There's something deeply eerie about that observation. Humanity spent most of its history wondering whether planets even existed around other stars. Then, within just a few decades, we advanced far enough to witness one dying, not through imagination, not through computer animation, through measurements, data, light crossing unimaginable distances before finally reaching telescopes here on Earth. Sometimes astronomy feels less like looking outward and more like overhearing private conversations between enormous objects. What makes all this even stranger is that planets like WASP-12b probably were not born where we find them today. That's one of the biggest clues that planetary systems are far more chaotic than they first appear. Gas giants are generally believed to form farther away from stars where temperatures are cool enough for large amounts of gas and ice to accumulate. In our own solar system, Jupiter formed far beyond the warm inner region where Earth resides. That distance mattered. Closer to the Sun, intense heat would have made Jupiter's formation difficult. So how did a giant world like WASP-12b end up practically brushing against its star? Astronomers suspect it migrated inward over time. Perhaps interactions with other planets destabilized its orbit. Perhaps gravitational forces within the early system slowly dragged it closer. Either way, at some point, this enormous world appears to have crossed a dangerous threshold. Too close. There is a certain dark irony in that phrase, because distance in space determines almost everything. Too far from a star and a world freezes into silence. too close and the star begins to consume it. Earth survives because it occupies a relatively narrow middle ground, a stable compromise, which becomes more impressive the longer astronomers search the galaxy. And the galaxy, it turns out, is full of places where compromise failed spectacularly. Some exoplanets orbit 2 stars at once, some drift freely through space without any star at all, some rain molten glass sideways in supersonic winds. One known world may even contain clouds rich in vaporized metals. Space is not particularly interested in moderation. That realization has changed astronomy profoundly over the last few decades. Before exoplanets were discovered, many scientists quietly assumed our solar system was fairly typical. Now we know it may actually be somewhat unusually orderly. The universe seems to enjoy extremes, and perhaps that's why WASP-12b fascinates astronomers so much. It sits near the edge of what planets can survive. A little closer to its star and it might already have been destroyed entirely. A little farther away and it might have remained stable for billions more years. Instead, we happen to exist during the era where the process is actively unfolding. That timing alone feels extraordinary. Human civilization is tiny compared to cosmic timescales. Recorded history barely covers a few thousand years. Modern astronomy occupies only a sliver of that. Yet somehow we developed telescopes at precisely the right moment to notice a distant world mid-destruction. It's rather like arriving at a beach just in time to witness a sandcastle collapsing into the tide. Except the sandcastle is larger than Jupiter, and the tide is a star. The star itself, known as WASP-12, is not especially unusual at first glance. It's somewhat larger and hotter than our Sun, sitting quietly in the constellation Auriga. If you looked at it from far enough away, nothing about it would immediately suggest planetary catastrophe, which is another strangely human lesson the universe keeps teaching us. Disaster does not always announce itself dramatically. Sometimes destruction happens beneath an appearance of calm. In fact, if you could somehow stand far outside this distant system and watch it safely from afar, the scene might initially appear beautiful. A bright star, a giant planet circling rapidly nearby, light reflecting across swirling gases. Only after closer inspection would the violence become apparent, the atmosphere boiling away, the planet deforming under gravity, the orbit slowly shrinking, an ending already underway. And even that ending unfolds at cosmic speed rather than human speed. No giant explosion, no sudden disappearance, just a gradual draining away across millions of years. The universe often prefers patience over spectacle. That idea can feel oddly calming at night. We spend so much of our lives surrounded by urgency, notifications, deadlines, timers counting down, yet almost everything truly enormous moves slowly. Stars burn slowly, galaxies rotate slowly. Even destruction in space usually unfolds with immense patience. A planet can spend millions of years falling apart. And somewhere in that thought, there's a strange invitation to breathe more slowly ourselves. Of course, breathing on WASP-12b would be an exceptionally bad idea. For one thing, there is no solid surface in the normal sense. Like Jupiter, it is primarily made of gas. Descending into it would mean sinking through increasingly dense layers of superheated atmosphere under crushing pressure. And unlike Jupiter, where upper cloud temperatures are extremely cold, this world exists under relentless stellar bombardment. The star fills an enormous portion of the sky. Day and night, as we understand them, barely function because the planet is tidally locked. One side always faces the star, the same side forever enduring permanent daylight, the opposite side remaining in perpetual darkness. Even that division is not peaceful. Winds scream across the planet, transporting heat around the globe at astonishing speeds. The atmosphere itself becomes a machine driven by extreme temperature differences, and overhead, always overhead, hangs the star responsible for the entire nightmare. Not angry, not malicious. Stars don't hate planets. gravity simply follows rules, which may be one of the most unsettling truths in astronomy. Catastrophe in space usually isn't personal. No cosmic villain chooses these outcomes. Objects simply obey physics with absolute consistency. Move too close to a star and heat increases. Move closer still and tidal forces intensify. Closer again, and eventually the star begins stripping material away. No drama, no cruelty, just consequences. And perhaps that's partly why stories like WASP-12b feel strangely compelling. They remind us the universe is neither gentle nor harsh in human terms. It simply is. Still, for all its violence, there's also something mesmerizing about this doomed world. A giant planet glowing in the darkness while slowly dissolving into its parent star. An entire atmosphere unravelling under impossible heat. A system balanced temporarily between existence and destruction. It almost sounds fictional. Yet tonight, while Earth turns quietly beneath sleeping cities and dim apartment lights and distant passing trains, this planet continues its final spiral. Orbit after orbit, year after year, losing itself piece by piece. Let's move a little closer now to the planet itself, because before we can understand why WASP-12b is falling apart, we should probably understand what it actually is. And as it turns out, the answer is already fairly strange before the destruction even begins. At first glance, astronomers classify WASP-12b as a gas giant. That places it in the same broad family as Jupiter and Saturn in our own solar system. Massive planets made mostly of hydrogen and helium, with deep atmospheres instead of solid surfaces. If you tried to land on one, you would not find rocky ground waiting beneath your feet. You would simply continue descending into thicker and hotter layers of gas, until pressure and temperature became catastrophic. So in that sense, WASP-12b initially sounds familiar. A big gas giant orbiting a star. Fairly standard cosmic behaviour. Then the details begin arriving one by one. The planet is about 1.9 times the mass of Jupiter. Its diameter is even larger. Its atmosphere is inflated by heat to such an extent that the entire world appears swollen, almost bloated under the intense radiation of its nearby star. If Jupiter is a sturdy cold giant comfortably resting in the outer solar system, then WASP-12b is more like a giant marshmallow held too close to a fire, and that fire is extremely close. The distance between WASP-12b and its star is only around 3 million kilometers. Now, in ordinary life, 3 million kilometers sounds enormous because humans are wonderfully bad at processing astronomical distances. But on the scale of planetary systems, that distance is astonishingly tiny. Mercury, the closest planet to our Sun, stays roughly 58 million kilometers away. WASP-12b orbits nearly 20 times closer to its star than Mercury does to ours. That is not close in the casual sense. That is practically touching the stove close. In fact, if WASP-12b existed inside our solar system, it would orbit well inside Mercury's path. It would be so close to the Sun that the entire concept feels slightly unreasonable. And yet, there it is. One of the odd things about exoplanets is how quickly they force astronomers to abandon intuition. The solar system teaches us certain patterns, then distant worlds arrive and casually ignore all of them. Before exoplanets were discovered, many planetary scientists assumed giant gas planets had to remain far from stars because that's where giant planets existed in our own system. Jupiter, Saturn, Uranus, Neptune. All cold, all distant. Then astronomers began finding hot Jupiters, huge planets hugging their stars so tightly that their orbital periods lasted only days. At first, some scientists genuinely suspected the data must be wrong. The planets seemed too strange to be real. But observation after observation confirmed it. The galaxy was full of giant planets parked in places they probably should not have survived. And among hot Jupiters, WASP-12b quickly became one of the most extreme examples ever found. Part of what makes the planet so fascinating is that it almost behaves less like a stable world and more like a system under active stress. Imagine spinning a ball of dough too quickly while holding it close to a strong fan heater. The dough softens, stretches, and deforms. That's roughly the situation here, except the dough is a planet larger than Jupiter, and the heater is an entire star. The gravitational forces acting on WASP-12b are so intense that the planet is no longer perfectly spherical. Astronomers believe it has become noticeably stretched into an egg-like shape. That stretching happens because gravity weakens with distance. The side of the planet facing the star experiences a stronger pull than the far side. On Earth, we experience smaller versions of this effect through ocean tides caused mostly by the moon, but Earth's tides are relatively gentle. Oceans rise and fall a few meters. On WASP-12b, the entire planet is experiencing tidal distortion. The world itself is being pulled out of shape, and because gas giants are not rigid like rocky planets, they respond dramatically to these forces. Their atmospheres can expand outward more easily. Heat penetrates deeply. Material begins escaping. There's something slightly unsettling about imagining a planet losing the structural argument against gravity. Jupiter survives comfortably because it stays far enough from the Sun for equilibrium to hold. WASP-12b crossed into territory where equilibrium started failing. Astronomers think the planet may already fill what's called its Roche lobe. That's an important concept with a surprisingly dramatic name. A Roche lobe is essentially the region around an astronomical object where its own gravity dominates and keeps material gravitationally bound. If a star or planet expands beyond this invisible boundary, material can spill away toward another object nearby. And that is exactly what seems to be happening here. The atmosphere of WASP-12b is leaking into space, not explosively, not violently in the cinematic sense, more like a slow cosmic overflow. The star is gradually pulling gas away from the planet and absorbing it, which means this entire system resembles something astronomers usually associate with stars rather than planets. In close binary star systems, one star can siphon material from another. Watching a star consume a planet in a similar way feels strangely intimate, like planetary boundaries have begun dissolving. Even the temperature numbers sound unreal. The dayside temperature of WASP-12b reaches around 2,500 to 3,000 degrees Celsius, depending on the atmospheric layer being measured. That is hotter than many types of lava, hotter than the melting point of numerous metals. At those temperatures, chemistry behaves differently. Molecules break apart. Atoms become ionized. The atmosphere glows from heat alone. If you could somehow float above the planet safely, which you absolutely could not, the sky would likely appear unlike anything humans naturally evolved to imagine. There would be no soft blue atmosphere, no familiar clouds drifting peacefully across a horizon. The star itself would dominate everything, blazing enormously overhead while the atmosphere shimmered under impossible heat. And because the planet orbits so closely, it has likely become tidally locked. That means one side always faces the star. The same hemisphere receives permanent daylight forever. Meanwhile, the far side remains locked in endless night. This happens because gravity gradually synchronizes rotational periods over time. Our moon is tidally locked to Earth, which is why we always see the same lunar face. But on WASP-12b, tidal locking creates a far more dramatic situation because of the planet's closeness to the star. One hemisphere absorbs relentless stellar energy continuously without relief. Still, despite that permanent heating, the night side is not entirely cold because the atmosphere redistributes heat through enormous winds. And when astronomers say winds here are fast, they mean genuinely absurdly fast. Thousands of kilometers per hour. Supersonic atmospheric flows carrying heat from one side of the planet to the other in an endless struggle for balance. Earth storms suddenly begin looking rather modest by comparison. It's strange to realise that worlds can exist where even the atmosphere feels overworked. One detail scientists find especially interesting is the planet's unusually dark appearance in certain wavelengths of light. Observations suggest WASP-12b absorbs a remarkable amount of incoming starlight instead of reflecting it back into space. In visible light, the planet may appear almost black, not because it's cold or empty, quite the opposite. The atmosphere is so hot and complex that it traps enormous amounts of radiation, a dark world glowing with internal heat while orbiting a blazing star close enough to be slowly consumed. If this sounds less like a normal planet and more like an astrophysical warning sign, that's understandable. And yet the system obeys perfectly ordinary physics. That's another recurring lesson in astronomy. Extreme objects often arise not because different laws apply, but because familiar laws are pushed to extraordinary limits. Gravity always pulls, heat always transfers, motion always follows orbital mechanics. The universe simply explores combinations humans never expected. In many ways, exoplanet science became a humbling exercise precisely because of this. Astronomers spent centuries building theories around one planetary system, our own. Then suddenly thousands of others appeared, revealing that nature is vastly more creative than human assumptions. There are planets denser than iron, planets lighter than cork relative to their size, planets orbiting dead stars, planets with years shorter than Earth days, planets drifting alone through interstellar darkness without any star at all. And somewhere within this enormous catalogue of cosmic oddities sits WASP-12b, slowly dissolving into its parent star. It's hard not to picture the planet as exhausted somehow. Not emotionally, of course. Planets do not suffer. But visually, scientifically, structurally, the world appears under relentless strain. Everything about it reflects imbalance. Too much heat, too much gravity, too much proximity, a gas giant living beyond safe orbital limits. And perhaps that's partly why people become fascinated by worlds like this. Extreme planets force us to reconsider what a planet even is. As children, many of us first learn about planets through neat classroom diagrams. Small rocky worlds near the sun, large gas giants farther away, circular orbits, stable arrangements, comfortable order. Then astronomy advances and reveals that the universe often prefers chaos with just enough structure to keep things interesting. Some hot Jupiters orbit so close to their stars that their upper atmospheres evaporate continuously. Others appear inflated far beyond expected sizes. Some may eventually spiral inward completely and vanish. WASP-12b might represent a temporary phase in planetary evolution, rather than a long-term stable configuration. That idea is important because it means we may be witnessing a planetary category during its final stage. Astronomically speaking, this system may not last much longer. Now, not much longer in cosmic terms still means millions of years, so there's no urgent need to update your calendar. But compared to ordinary planetary lifetimes, that's relatively brief. Earth has survived around 4.5 billion years. Jupiter likely will continue orbiting for billions more. WASP-12b may already be running out of time, and astronomers suspect the orbit itself is shrinking. That detail is especially unsettling. The planet is not merely close to its star. It appears to be moving even closer over time. Tiny changes in orbital timing suggest the world may be spiraling inward gradually as tidal interactions drain orbital energy away. The process is subtle but measurable. Every orbit brings the planet fractionally nearer. Closer heat, closer gravity, closer destruction. There's something deeply eerie about orbital decay because it transforms an orbit from a stable path into a countdown. Not a dramatic countdown with flashing red numbers and alarms. A quiet one. Millions of years long. The kind only the universe has patience for. Of course, one comforting detail is that nothing remotely similar threatens Earth. The planets in our solar system occupy stable orbits shaped over billions of years. Jupiter will not suddenly plunge into the Sun. Earth will not begin evaporating next Tuesday. Although if your internet provider goes down tomorrow, it may briefly feel otherwise. Still, studying worlds like WASP-12b helps scientists understand planetary systems more broadly. Extreme cases reveal physical processes more clearly. Heat transfer, atmospheric escape, orbital migration, tidal forces. Nature performs experiments on scales humanity never could. Astronomers simply watch carefully enough to learn from them, and that learning process itself is remarkable. Think about what's actually happening when scientists study this planet. Light leaves a distant star system more than 1,000 light-years away. That light travels across interstellar darkness for centuries. Eventually, a tiny fraction reaches Earth where telescopes analyze minute fluctuations and spectral signatures. From those faint signals, humanity reconstructs an entire alien world. Its size, its orbit, its temperature, its atmosphere. Even signs that it is actively disintegrating. That ability still feels almost magical despite being entirely scientific. Especially at night. Especially when you stop and remember that humans evolved on one small rocky planet, throwing spears at things and occasionally eating berries of questionable judgment. And now we measure the death of distant worlds, slowly, patiently, orbit by orbit. Back in the early 1990s, astronomers were still living in a slightly humbling situation. Humanity had spent thousands of years staring at the night sky, inventing telescopes, mapping constellations, calculating planetary orbits, and confidently discussing the structure of the universe. Yet we'd never actually confirmed the existence of a single planet orbiting another normal star. It sounds almost unbelievable now because exoplanets have become so common in astronomy news that people casually scroll past headlines about lava worlds and diamond planets while waiting for coffee. But for most of human history, planets beyond our solar system existed mainly as educated guesses. Most scientists assumed they had to exist. After all, it would have been rather strange if the universe created exactly one planetary system and then simply stopped trying. But assumption is not evidence, and astronomy has a long tradition of demanding proof before getting too comfortable. Then, in 1995, everything changed. That year, astronomers announced the discovery of 51 Pegii b, the first confirmed planet orbiting a sun-like star, and the discovery immediately surprised everybody because the planet itself made almost no sense. According to prevailing theories, it was a giant gas planet orbiting extremely close to its star, a hot Jupiter. At first, astronomers wondered if the result might somehow be mistaken, because giant planets were not supposed to sit that close to stars. In our own solar system, gas giants live far away in the colder outer regions where icy materials and gas could accumulate during formation. But the evidence held, and suddenly the universe became much stranger. Over the following years, astronomers began discovering more and more of these bizarre close-orbiting worlds. Some circle their stars in mere days, others appeared physically inflated by heat. Some experienced temperatures so extreme that ordinary atmospheric chemistry broke down entirely. Then eventually, among this growing catalogue of impossible places, astronomers encountered WASP-12b. And fittingly for such a dramatic world, its discovery came from a project with a wonderfully practical name, WASP. That stands for the Wide-Angle Search for Planets, which sounds slightly less intimidating once expanded, though still impressively determined. The name also creates the amusing image of astronomers patiently scanning the heavens, while armed with what sounds suspiciously like a giant cosmic insect. The WASP project itself was designed to solve a difficult problem. Planets are incredibly hard to detect directly, because stars overwhelmingly outshine them. Trying to photograph an exoplanet beside its star is a little like trying to photograph a firefly hovering next to a lighthouse from thousands of kilometers away. The star dominates everything, so astronomers needed indirect methods, and one of the most successful methods ever invented turned out to rely on shadows. Not literal shadows drifting across walls or landscapes, of course, more like tiny dips in starlight. Here's the basic idea. If a planet passes directly between its star and Earth, the planet blocks a very small fraction of the star's light. The star dims ever so slightly for a short time before returning to normal brightness once the planet moves away again. This event is called a transit, and if those dips happen repeatedly at regular intervals, astronomers can infer that a planet is orbiting the star. Simple in principle, exceptionally difficult in practice. The changes in brightness are tiny, often less than 1%. Imagine staring at a bright lighthouse from across an ocean and trying to notice whether someone briefly waved a small moth in front of it. That is roughly the level of sensitivity astronomers needed. Still, technology improved rapidly, and transit surveys became astonishingly effective at discovering planets. The WASP project used arrays of cameras positioned in different hemispheres to monitor huge sections of the sky simultaneously. Night after night, these telescopes observed thousands upon thousands of stars, looking patiently for a tiny periodic flickers. Most stars remained steady, some fluctuated naturally, a few contained planets, and in 2008, astronomers announced the discovery of WASP-12b. At first, it already appeared unusual. The orbital period alone immediately stood out. The planet completed one orbit in just over a single Earth day. That meant it had to orbit extraordinarily close to its star. Then researchers began measuring its size and mass. Huge, bloated, superheated. A giant planet pushed dangerously near stellar territory. And the more scientists studied it, the stranger it became. There's something quietly fascinating about the way astronomy often works. Discoveries rarely arrive fully understood. Instead, astronomers notice one odd clue, then another, until eventually an entire picture begins emerging from scattered pieces of evidence. A transit reveals the planet's size relative to the star. Spectroscopy reveals atmospheric composition. Orbital timing reveals gravitational interactions. Temperature measurements reveal heat redistribution. Gradually, an invisible world becomes real. And that process still feels almost miraculous when you stop to think about it. Nobody has visited WASP-12b. Nobody has photographed it directly in sharp detail. Everything we know comes from light, tiny fluctuations, subtle spectral fingerprints, a distant star dimming by a fraction of a percent. Humanity has become remarkably good at extracting meaning from faint signals. One reason hot Jupiters like WASP-12b were discovered relatively early is actually quite practical. They're easier to detect than many smaller planets. Large planets block more starlight during transits. Close planets transit more frequently, and their gravity causes stronger measurable effects on their stars. So even though astronomers eventually became more interested in smaller Earth-like worlds, the first wave of exoplanet discoveries was dominated by giant planets in absurdly close orbits. In other words, the galaxy introduced itself with its loudest and least subtle residents, rather like opening a door or expecting polite conversation and immediately finding somebody wrestling a crocodile in the living room. Hot Jupiters are difficult to ignore. Once WASP-12b entered scientific databases, follow-up observations intensified quickly because the planet's characteristics made it an ideal laboratory for extreme planetary physics. Its large size helped. Its close orbit helped. Its extreme heat helped. And importantly, the planet transited a relatively bright star, making detailed measurements easier. Astronomers soon began using larger observatories and eventually even space telescopes to investigate the system further. That's when things became especially interesting. One major breakthrough involved studying the planet's atmosphere through transit spectroscopy. This technique is wonderfully clever. When a planet passes in front of its star, a tiny portion of starlight filters through the outer layers of the planet's atmosphere before reaching Earth. Different atoms and molecules absorb different wavelengths of light, leaving characteristic signatures behind. By analysing those signatures, astronomers can determine what gases exist in the atmosphere, which means scientists can study alien atmospheres across interstellar distances. Again, this remains one of those facts that feels slightly unreasonable even though it is completely true. And when researchers examined WASP-12b, they found signs of atmospheric escape. Material appeared to be extending outward far beyond the expected planetary boundary. Hydrogen and other gases were leaking away into space. The planet was losing mass. At that point, WASP-12b stopped being merely a hot Jupiter and became something more dramatic, a world actively undergoing destruction. One especially important set of observations came from the Hubble Space Telescope. Using ultraviolet observations, astronomers detected evidence that the planet's atmosphere stretched outward in a huge cloud surrounding the system. The escaping gas formed an extended envelope around the planet. Imagine steam rising from boiling water, except the steam is planetary atmosphere and the boiling pot is larger than Jupiter. And unlike steam from a kettle, this atmosphere is not cooling and condensing safely nearby. It is being stripped away by stellar forces and lost into space. The scale becomes difficult for human brains to process comfortably. Another curious detail emerged when scientists studied the planet's reflectivity. WASP-12b appeared incredibly dark in visible light, reflecting very little of the starlight hitting it. This surprised astronomers because many gas giants possess reflective cloud layers. But on this planet, temperatures are so high that ordinary cloud chemistry fails. Instead of bright reflective clouds, the atmosphere absorbs tremendous amounts of radiation. A dark world heated to glowing temperatures while shedding atmosphere into space. At some point, the line between planet and astrophysical cautionary tale becomes slightly blurry. One thing astronomy repeatedly teaches is that the universe rarely cares whether environments seem survivable or reasonable to us. Physics explores every available possibility. Sometimes those possibilities include worlds where the atmosphere literally evaporates under stellar bombardment. And through all of this, astronomers continued refining measurements of the system. The star itself, WASP-12, lies roughly 1,400 light-years away in the constellation Auriga. Slightly larger and hotter than our Sun, it initially appeared fairly ordinary. But its relationship with the planet is anything but ordinary. Researchers eventually realized tidal interactions between the star and planet might actually be altering the orbit measurably. That possibility created enormous excitement because orbital decay is difficult to observe directly. Planetary systems usually evolve across timescales far longer than human civilization, but WASP-12b appeared extreme enough that astronomers might catch the process happening in real time, or at least real time by astronomical standards. Observations suggested the planet's orbit may be shrinking gradually. Tiny changes in transit timing hinted that the world was spiraling inward. That detail transformed the discovery from interesting to genuinely remarkable. Humanity may be watching a planet die, not metaphorically, physically. Its orbit tightening, its atmosphere escaping, its structure distorting under tidal stress, and all of this inferred from tiny changes in distant starlight. Sometimes astronomy feels less like observing objects and more like detective work performed across impossible distances. What makes the discovery process even more impressive is how collaborative modern astronomy has become. Different telescopes, different countries, different teams of scientists all contributed observations over time. Ground-based observatories tracked transits. Space telescopes analysed atmospheres. Researchers refined orbital models. Computers processed enormous data sets. And gradually, through collective effort, an increasingly detailed portrait emerged of a world humanity will almost certainly never physically visit. That ability to understand unreachable places may be one of science's quietest achievements. Especially late at night, there's something deeply calming about remembering that curiosity itself can travel farther than bodies ever will. Humans remain confined to one small planet for now, yet our measurements reach across galaxies. Our equations describe invisible worlds. Our telescopes notice atmospheres escaping around distant stars. All while most of us are simultaneously struggling to remember where we left our phone charger. Civilization contains multitudes. Of course, discovering WASP-12b also raised enormous questions about planetary formation. How did a giant gas planet end up so catastrophically close to its star? Did it form there? Probably not. Did it migrate inward over time? Most likely. And if migration happens commonly, what does that mean for the stability of planetary systems in general? Suddenly planetary systems looked less permanent and more dynamic. Worlds move, orbits shift, gravity rearranges architecture over millions of years. The calm stability of our solar system began looking less universal and more fortunate. That realization subtly changed humanity's perspective on Earth too. We often treat our planetary conditions as normal simply because they are familiar. But exoplanet discoveries revealed that stable, moderate worlds may be far rarer and more delicate than once assumed. Some planets freeze, some burn, some fall into stars, some may never settle into stable climates at all. Earth occupies a surprisingly comfortable position in an often uncomfortable universe, and perhaps that's partly why discoveries like WASP-12b resonate so strongly. Extreme worlds make ordinary ones feel newly precious. A stable orbit suddenly seems remarkable. A moderate climate suddenly feels unusual. A peaceful night sky begins looking less guaranteed and more improbable. Still, the universe clearly enjoys building dangerous systems, and dangerous systems often become scientifically irresistible. Astronomers love extremes because extreme conditions reveal hidden physics more clearly. Processes that happen slowly elsewhere become accelerated and observable. On WASP-12b, tidal distortion becomes obvious, atmospheric escape becomes measurable, orbital decay may become detectable within human timescales. The planet behaves almost like a cosmic laboratory dedicated entirely to demonstrating what happens when a gas giant drifts too close to a star. Here on Earth, time feels steady enough that we rarely stop to think about it. Morning arrives, afternoon drifts by, evening settles in quietly. A year passes one season at a time, measured in birthdays, changing weather, and those moments when you suddenly realize the grocery store has already started selling holiday decorations absurdly early again. Our planet takes 365 days to orbit the Sun. That journey feels normal because it's all we've ever known. But one of the strangest things astronomers discovered after finding exoplanets was just how wildly different a year can become elsewhere in the universe. On Mercury, a year lasts 88 Earth days. On Neptune, a single orbit takes 165 Earth years. And then there is WASP-12b, where an entire year passes in about 26 hours. Not 26 days, not 26 weeks, barely more than one Earth day. If you lived there, which would admittedly involve surviving temperatures capable of melting several household appliances simultaneously, you would celebrate a new year almost every morning. Imagine trying to maintain a calendar under those conditions. You wake up, make coffee, suddenly it's March. By dinner, astronomically speaking, you're approaching autumn. The sheer speed of the orbit is difficult to picture because humans instinctively associate planets with slow, majestic motion. We imagine worlds drifting gently around stars over vast periods of time. Even the word orbit sounds calm. But WASP-12b is not drifting, it is racing. The planet moves around its star at roughly 230 kilometers per second. That is over 800,000 kilometers per hour. At that speed, you could circle Earth in under 3 minutes. Of course, there would be certain atmospheric complications. Still, the scale of motion here is extraordinary. The planet is locked into an unbelievably tight gravitational dance with its star, orbiting so closely that the entire system behaves less like the calm architecture of our solar system and more like two objects caught in a dangerous embrace. And because the orbit is so small, the star dominates the sky completely. If you could somehow observe the system safely from the planet's upper atmosphere, the star would appear enormous overhead. Not like our sun viewed from Earth, a bright disk crossing a blue sky. This star would feel overwhelming. The light alone would reshape your entire sense of scale. Astronomers estimate the planet orbits only about 3 million kilometers from the star's surface. That may still sound large because human brains are wired for parking lots and staircases rather than orbital mechanics, so let's put it differently. The diameter of the star itself is not much smaller than the entire orbit. The planet circles incredibly close to the stellar surface, close enough that gravity distorts it, close enough that heat inflates its atmosphere, close enough that material is literally escaping. There's a certain recklessness to the arrangement, although of course planets are incapable of bad decision-making. Gravity arranged this system according to physics, not judgment. Still, from a human perspective, the orbit feels almost alarmingly intimate, like watching someone stand much too close to a bonfire while insisting they're perfectly comfortable. One particularly strange consequence of such a short orbit is that ordinary ideas about days and nights begin breaking down. Here on Earth, our experience of time is built around rotation. The planet spins once every 24 hours, producing sunrise and sunset. Our ancestors structured civilizations around those cycles. Sleep, work, migration, agriculture, even emotions became tied to the rhythm of daylight. But on WASP-12b, things are very different. The planet is almost certainly tidally locked. That means one side permanently faces the star, while the opposite side permanently faces away. The same thing happened to Earth's moon long ago. The moon rotates at exactly the same rate that it orbits Earth, which is why we always see the same lunar face. But the consequences become much more dramatic when a giant gas planet orbits extremely close to a blazing star. On WASP-12b, there may be no traditional sunrise or sunset at all. One hemisphere exists in endless daylight, the other in permanent darkness, and between them lies a transition zone where temperatures and atmospheric conditions shift violently. It's strange to imagine a world without moving shadows. No evening, no dawn, no gradual fading of daylight into night. Just constant exposure, the star hanging motionless in the sky forever. Humans evolved beneath rotating skies, so permanent daylight feels psychologically unsettling even in imagination. Our minds expect change overhead. Clouds move, the sun travels, stars emerge at night, time becomes visible through motion. But on a tidally locked world, the sky itself grows strangely fixed, and yet despite this apparent stillness, the atmosphere remains incredibly active because heat redistribution becomes essential for survival of the planet's structure. The day side absorbs astonishing amounts of stellar energy continuously. Temperatures soar above 2,500 degrees Celsius. That heat then drives enormous winds transporting energy toward the night side. Astronomers believe these winds move at several kilometers per second. Not ordinary storms, planet-wide atmospheric violence. The entire atmosphere behaves like a machine desperately attempting to balance impossible temperature extremes. One fascinating detail about hot Jupiters is that they challenge ordinary weather concepts completely. On Earth, weather systems are influenced by oceans, mountains, seasonal heating and planetary rotation. But gas giants like WASP-12b possess entirely different atmospheric dynamics. There are no continents, no oceans in the earthly sense, no stable ground beneath the clouds, just deeper and deeper layers of gas under rising pressure and temperature. And because the planet is heated externally by its star and internally by tidal forces, the atmosphere becomes astonishingly complex. Astronomers suspect some hot Jupiters may contain clouds of vaporized metals or exotic minerals condensing under bizarre conditions. In cooler layers, compounds impossible on Earth might briefly form before being blasted apart again by heat elsewhere. Chemistry on such worlds becomes less like familiar weather and more like industrial physics operating at planetary scale. It's oddly humbling that the universe can produce environments so extreme that ordinary human intuition simply stops functioning properly, and yet the orbital mechanics themselves remain beautifully simple. The closer a planet is to a star, the faster it must move to avoid falling inward. That's gravity's bargain. Move closer, and orbital speed increases dramatically. Mercury moves faster around the Sun than Earth does. Earth moves faster than Jupiter, and WASP-12b moves at astonishing speed because it lives practically on top of its star. The physics involved were first formalized centuries ago by Johannes Kepler and later explained more deeply through gravity by Isaac Newton. Even today, planetary motion follows those same gravitational rules with remarkable consistency. There's something comforting about that consistency. No matter how strange exoplanets become, gravity remains reliable. Perhaps slightly over-enthusiastic in this particular system, but reliable. Another curious effect of this short orbit involves tidal heating. Most people associate planetary heating with sunlight alone, but gravity itself can generate enormous amounts of heat through distortion. A good example exists within our own solar system. Jupiter's moon experiences intense volcanic activity because Jupiter's gravity stretches and compresses the moon continuously as it orbits. That mechanical stress produces internal heating. WASP-12b experiences tidal forces vastly stronger. The planet is constantly being stretched by stellar gravity. That repeated deformation likely generates additional heat deep inside the planet, contributing to its inflated structure. In other words, the planet is heated both from outside and within. It's being roasted and kneaded at the same time. Cosmic baking rarely ends well. One especially interesting aspect of such rapid orbits is how stable they initially appear despite being inherently dangerous long-term. From moment to moment, the planet follows a perfectly predictable path. Every orbit completes on schedule. Gravity balances motion precisely. But over millions of years, subtle energy transfers accumulate. Tidal interactions slowly alter the orbit. The star raises tides within the planet. The planet raises tides within the star. Energy dissipates. Angular momentum shifts. Gradually the orbit may shrink. This is one of the eerie things about astrophysics. Systems can appear stable on human timescales, while actually evolving toward destruction on cosmic timescales. A planet can survive comfortably for thousands of generations while still being doomed eventually. Although, to be fair, that description also applies to several office printers. Astronomers studying transit timing have found evidence suggesting WASP-12b may indeed be spiraling inward slowly. The changes are tiny, minutes spread across years of observation, but measurable, and those measurements matter enormously because observing orbital decay directly is rare. Most planetary evolution occurs far too slowly for humans to notice, but this world is extreme enough that the process may reveal itself within modern astronomy itself. We may actually be watching a planet lose its battle against gravity. That realization transforms the orbit from an interesting statistic into a narrative. Every 26-hour year becomes another step inward, another orbit closer to destruction, another pass beside the star stripping away atmosphere. There's something strangely haunting about imagining a year not as renewal but as erosion. On Earth, a year usually symbolizes continuity, another orbit, another cycle of seasons, another return to familiar skies. But for WASP-12b, each orbit may carry the planet fractionally closer to its end. And because the orbit is so short, these changes accumulate rapidly. Thousands upon thousands of years pass in what would barely register as geological time on Earth. 1 million Earth years equals over 350 million local years there. That number becomes almost absurd when you pause to think about it. Civilizations on Earth rise and fall across a few thousand years. Meanwhile, this planet completes millions upon millions of orbits around its star in the same span. Time itself begins feeling different when orbital scales change that dramatically. Astronomy has a wonderful habit of revealing that many concepts humans treat as fixed are actually local experiences. A year is not universal. A day is not universal. Even sunrise is not universal. These are planetary circumstances rather than cosmic constants. Some worlds have years shorter than days. Some have permanent daylight. Some wander through eternal darkness between stars. The universe contains far more variety than human cultures ever needed to prepare for. And yet, despite all this extremity, there's something oddly mesmerizing about the regularity of the orbit too. Every 26 hours, the planet returns. Gravity keeps its schedule with extraordinary precision. The star waits. The planet circles. Again, again, again. A giant overheated world endlessly rushing around the object destroying it. If that sounds almost tragic, it's probably because humans instinctively attach emotional narratives to repeating patterns. We see cycles and imagine meaning. But stars and planets operate without intention. The system persists simply because the mathematics permit it, at least for now. One thing astronomers find especially valuable about these extremely short-period planets is that they provide lots of observational opportunities. Since WASP-12b transits frequently, scientists can gather large amounts of data relatively quickly. A planet orbiting once every 10 years might transit only a few times across an astronomer's entire career. This world transits constantly. Every few days, telescopes can collect more information, more atmospheric measurements, more timing data, more evidence of orbital evolution. In a way, the planet's frantic orbit makes it easier for humanity to study. Which feels slightly unfair, really. The universe built one of the most physically stressful environments imaginable, then also made it scientifically convenient. Astronomers naturally were delighted. Still, behind all the measurements and orbital calculations lies something quietly astonishing. This entire system exists. A giant planet larger than Jupiter whipping around its star in barely more than a day while being stretched apart by gravity and slowly consumed. And somewhere tonight, while Earth continues its comparatively calm orbit around the Sun, that distant world is already racing through another year, another complete revolution, another close pass beside the star, another tiny step toward eventual destruction. There is something almost uncomfortable about how close WASP-12b sits to its star. Not scientifically uncomfortable. Astronomers are usually thrilled by uncomfortable systems because uncomfortable systems tend to produce excellent data. But on a human level, the arrangement feels wrong in the same way a chair balanced on two legs feels wrong. Your instincts immediately suspect consequences, and in this case, the consequences are very real. Because WASP-12b is not merely hot. Plenty of planets are hot. Venus is hot enough to melt lead. Mercury becomes scorching under direct sunlight. Even Earth occasionally produces parking lots capable of psychologically damaging bare feet. But this planet exists in a completely different category. Its temperatures rise above 2,500 degrees Celsius. At times, certain regions may approach 3,000 degrees. That is hot enough to melt iron, hot enough to vaporize many minerals entirely, hot enough that chemistry itself begins behaving in unfamiliar ways. The phrase, close to its star, stops sounding like an orbital detail and starts sounding more like a survival problem. One reason these temperatures become so extreme is simple geometry. Stars radiate enormous amounts of energy outward in every direction. The closer an object moves toward that energy source, the more concentrated the radiation becomes. Earth survives comfortably because it stays roughly 150 million kilometers from the Sun. That distance matters tremendously. If Earth orbited significantly closer, oceans would evaporate, atmospheric chemistry would destabilize. Surface temperatures would climb catastrophically, move much farther away, and the planet freezes instead. Habitability, it turns out, is largely a story about distance, and WASP-12b has abandoned all reasonable distance. At only about 3 million kilometers from its star, the planet absorbs an astonishing amount of radiation continuously. The energy flooding its atmosphere is difficult to overstate, because humans have no ordinary experience comparable to stellar heating on this scale. Even the word daylight becomes inadequate. The star would dominate the sky so completely that normal concepts of brightness lose meaning. There would be no comfortable sunlight, no golden evening glow, no soft dawn arriving gently through windows, only relentless irradiation. A permanent blast furnace hanging overhead. And unlike Earth, which rotates steadily and distributes solar heating across its surface, WASP-12b is likely tidally locked. One side permanently faces the star while the other remains in eternal darkness. That creates a world divided into extremes. The day side absorbs continuous stellar energy without interruption. No sunset ever arrives to cool things down. No nighttime recovery period exists. The atmosphere remains trapped under endless heating. Sometimes astronomy reveals environments so extreme they almost sound less like planets, and more like failed negotiations between gravity and thermodynamics. This is one of those places. Astronomers studying hot Jupiters originally wondered whether atmospheres under such intense radiation might simply evaporate away quickly. After all, gas giants are made mostly of hydrogen and helium, relatively lightweight elements that can escape more easily when heated enough. And on WASP-12b, the atmosphere is not merely heated, it is inflated. The planet has become physically swollen under thermal stress. The outer atmospheric layers puff outward because extreme temperatures increase pressure and expand the gas. In some ways, the entire world resembles an overheated balloon stretched dangerously near bursting conditions. Except instead of rubber, the planet consists of superheated atmospheric layers larger than Jupiter itself. And unlike a balloon, the problem here is not just internal pressure. Gravity is pulling from outside too. The star's immense gravitational field stretches the planet continuously. The side facing the star experiences stronger gravitational force than the far side, producing tidal distortion across the entire world. Earth experiences tides mostly in its oceans. WASP-12b experiences tides across its entire planetary structure. Imagine squeezing and stretching something constantly, while simultaneously heating it to extreme temperatures. Eventually material begins escaping, and that is precisely what astronomers believe is happening. The atmosphere of WASP-12b extends so far outward that stellar gravity actively strips gas away into space. This process is called atmospheric escape. On Earth, atmospheric escape happens too, but very slowly. Lightweight particles occasionally gain enough energy to leave Earth's gravity entirely. Over billions of years, planets can gradually lose atmospheric components this way. But on WASP-12b, the process is dramatically accelerated. The atmosphere is effectively boiling away. Not like water bubbling in a kitchen pot exactly, although that image is oddly useful. More like a giant sphere of superheated gas losing material continuously under relentless radiation and gravitational stress. Astronomers using the Hubble Space Telescope observed evidence that the escaping atmosphere extends far beyond the planet itself, forming a huge cloud around the system. Hydrogen gas trails outward into space. The star is feeding on the planet, slowly, steadily. And perhaps the strangest part is that this destruction remains surprisingly orderly. Human beings often imagine catastrophe as loud and sudden. Explosions, impacts, chaos unfolding dramatically in minutes or hours. But space frequently prefers patience. A planet can die gradually across millions of years. orbit after orbit, layer after layer. The universe has very little interest in dramatic pacing. One fascinating detail scientists discovered involves how dark the planet appears in visible light. Many gas giants reflect substantial amounts of incoming starlight due to clouds or atmospheric particles. Jupiter, for example, reflects beautifully. But WASP-12b absorbs most of the light striking it. It is one of the darkest exoplanets ever observed. That sounds slightly contradictory at first. How can something heated so intensely also appear dark? The answer involves atmospheric chemistry and temperature. The atmosphere is so hot that reflective cloud layers likely cannot form normally. Instead of bright clouds bouncing light back into space, radiation penetrates deeply into the atmosphere where it becomes absorbed. So the planet appears dark not because it lacks energy, but because it traps so much of it. A blackened, overheated world glowing with internal heat. There's something almost furnace-like about the description, and the heat affects more than just the atmosphere. Astronomers suspect tidal heating contributes additional energy deep inside the planet itself. The continuous gravitational stretching generated by the nearby star flexes the planet constantly, producing internal friction and heat. It's similar in principle to how bending a paperclip repeatedly makes it warm, except the paperclip is a giant planet, and the hand bending it is a star. The combined effect creates one of the most physically stressed worlds humanity has ever discovered. In some ways, WASP-12b exists near the edge of what a planet can survive. That edge turns out to be scientifically valuable because extreme environments reveal physical processes more clearly than calm, stable systems. On Earth, atmospheric escape occurs slowly. Here, it becomes measurable. In ordinary planetary systems, tidal distortion may be subtle. Here, it reshapes the entire planet. In stable systems, orbital evolution unfolds quietly over billions of years. Here, astronomers may actually detect orbital decay directly. The planet behaves almost like a demonstration model built specifically to show what happens when gravity pushes too far. Of course, too far in astronomy rarely means immediate destruction. Cosmic timescales remain enormous even during catastrophe. The planet is not about to vanish tomorrow morning. Although astronomically speaking, it is probably living on borrowed time. Researchers estimate the world may survive only a few million more years before tidal forces and atmospheric loss eventually destroy it completely. Now a few million years sounds comfortably distant from a human perspective, because humans become emotionally relaxed any time numbers exceed our tax paperwork lifespan. But cosmically speaking, that is relatively brief. Earth has existed for about 4.5 billion years. The Sun itself will survive billions more. Compared to ordinary planetary lifetimes, WASP-12b appears temporary, a giant world caught in a dangerous transitional stage. One reason this system fascinates astronomers so deeply is because it may reveal the eventual fate of many hot Jupiters. These planets probably did not form near their stars originally. Giant planets are thought to form farther out, where cold conditions allow large gas envelopes to accumulate, so something must move them inward later. Planetary migration likely reshapes many young systems. Gravitational interactions between planets or with disks of gas can alter orbits dramatically over time. Some planets stabilize safely, others move too close. And worlds like WASP-12b may represent the final stage of that inward migration process. A giant planet stranded fatally near its star. There's something slightly eerie about realizing that planetary systems are not fixed structures. We often imagine solar systems as permanent arrangements, stable, predictable, finished. But gravity keeps working forever. Orbits evolve, distances change, interactions accumulate. The solar system itself once looked very different billions of years ago. And elsewhere in the galaxy, planets are still moving into dangerous positions right now. Some may already be falling toward destruction. Others may have vanished long before humans evolved enough to notice. Astronomy can feel strangely archaeological in that way. Observing distant systems often means catching temporary moments within long, evolving stories. And because light takes time to travel, the system we see today is already ancient history. The light currently reaching Earth from WASP-12b left around the time the early Middle Ages were unfolding on Earth. While kingdoms rose and fell here, that light crossed interstellar darkness patiently before finally reaching telescopes centuries later. Astronomy constantly reminds us that observation itself involves time travel of a sort. We never see the universe as it is now, only as it was. Still, even ancient light carries remarkable detail. Astronomers can measure atmospheric composition, temperature distributions, orbital characteristics, and evidence of atmospheric escape, all from tiny fluctuations in distant starlight. Humanity has become astonishingly good at interpreting faint signals, especially considering many of us still occasionally forget why we walked into kitchens. One particularly intriguing aspect of extreme heating on WASP-12b involves chemical stability. At temperatures approaching several thousand degrees, molecules struggle to remain intact. Water vapor can dissociate. Complex compounds break apart. Atoms lose electrons. The atmosphere enters a regime where ordinary Earth chemistry begins failing entirely. This is no longer weather in the familiar sense. It is high-energy atmospheric physics operating continuously across planetary scale. And because the star bombards the atmosphere with ultraviolet radiation as well, upper layers become even more unstable. The entire world exists under conditions approaching physical exhaustion. There's a peculiar emotional effect that extreme exoplanets sometimes create. Instead of making Earth feel insignificant, they often make it feel unexpectedly gentle. A stable climate suddenly seems extraordinary. Moderate sunlight feels luxurious. The existence of oceans rather than vaporized minerals begins looking deeply fortunate. Compared to worlds like WASP-12b, Earth is astonishingly calm. Even our worst storms remain modest beside planetary atmospheres heated nearly to stellar conditions. And perhaps that's one reason people find exoplanets so mesmerizing late at night. They stretch perspective. They remind us how many possible versions of reality exist beyond human experience. Some worlds freeze beneath eternal darkness, some rain molten material, some wander starless through interstellar space, and some, like WASP-12b, orbit so dangerously close to their stars that survival itself becomes temporary. A giant world barely holding together under impossible heat. A planet existing at the edge of destruction. Gravity is usually described as the force that holds things together. Planets form because of gravity. Stars ignite because of gravity. Galaxies stay assembled because of gravity. So it feels slightly unfair that gravity can also become the thing tearing a planet apart. And yet that is exactly what's happening to WASP-12b. The planet is not simply hot, not simply orbiting quickly, not merely losing atmosphere. The entire world itself is being physically stretched by the immense gravitational pull of its nearby star. Astronomers believe the planet has become noticeably distorted, elongated into something more oval than spherical. Instead of a neat giant ball like Jupiter, WASP-12b may resemble an enormous droplet of softened material being pulled outward, like melted wax near a flame, or dough stretched too far by invisible hands. That image sounds dramatic, but the physics behind it are actually very straightforward. Gravity weakens with distance, that's the key idea. The side of the planet closest to the star experiences a stronger gravitational pull than the far side. Because WASP-12b orbits unbelievably close, the difference between those forces becomes enormous. And when gravity pulls harder on one side of an object than the other, tides happen. Now, on Earth, tides seem fairly gentle. The moon's gravity raises and lowers ocean levels over the course of the day. Beaches expand and shrink. Boats rise and fall quietly in harbours. Occasionally somebody's picnic becomes emotionally educational. Nothing too catastrophic. But tidal forces scale dramatically with proximity, move much closer to a massive object, and tides become far more intense. Near a black hole, tidal forces become so extreme they can literally tear stars apart. Astronomers even have a wonderfully alarming term for this process: spaghettification, which sounds far too cheerful for something involving violent gravitational destruction. Fortunately, WASP-12b is not being turned into spaghetti exactly. More like a giant overheated planetary egg under continuous gravitational stress. Still, the same basic principle applies. The star's gravity stretches the planet relentlessly, and unlike rocky planets, gas giants deform relatively easily because they lack rigid solid surfaces. Jupiter itself bulges slightly due to rotation. Saturn is visibly flattened at its poles. These worlds are fluid enough internally that gravity and motion reshape them continuously. But on WASP-12b, the effect becomes much more extreme because the planet sits so dangerously close to its star. The tidal forces are enormous. Imagine holding a water balloon very gently. Now imagine slowly pulling it from opposite ends while simultaneously heating it. Eventually the shape changes. That is roughly what's happening here, except the water balloon is nearly twice Jupiter's mass, and the heating source is an entire star. Astronomers suspect the planet may already fill or nearly fill something called its Roche lobe. This is one of those wonderfully strange astrophysical concepts that sounds fictional but describes something deeply important. A Roche lobe is essentially the region around an astronomical object, where its own gravity still controls material. Inside that region, gas remains gravitationally bound to the planet. But if the atmosphere extends too far outward, stellar gravity begins stealing material away, and on WASP-12b, that boundary appears dangerously close. The planet has become so inflated by heat and stretched by tides that parts of its atmosphere may already extend beyond safe gravitational limits. At that point, the star starts siphoning gas directly away, which means the stretching is not merely cosmetic. The distortion itself contributes to the planet's destruction. There's something quietly eerie about that. A planet becoming so physically strained that it can no longer fully hold on to itself. One especially interesting detail is that tidal forces don't merely distort shape externally. They also generate internal heat through friction. This process is called tidal heating. Every time the planet flexes under gravitational stress, energy dissipates internally as heat. It's somewhat similar to repeatedly bending a metal wire until it warms up, only on planetary scale. Jupiter's moon, Io, provides a famous example within our solar system. Io experiences intense gravitational pulling from Jupiter and neighbouring moons, which continuously flexes its interior. The result is extraordinary volcanic activity. Io is the most volcanically active object in the solar system because gravity needs it like dough. WASP-12b experiences tidal stress vastly stronger. The planet is being stretched constantly as it orbits its star. That stretching generates internal friction, which creates additional heat deep inside the planet. So the world is heated both externally by stellar radiation and internally by gravitational distortion. The entire system behaves like a giant cosmic torture test for planetary physics. And because the atmosphere is already expanded from extreme temperatures, the stretching effect becomes even more dramatic. The outer layers puff outward more easily, making atmospheric escape simpler. This creates a vicious cycle. Heat expands the atmosphere. Expansion weakens gravitational binding. Tidal forces stretch the atmosphere farther. Material escapes more easily. The planet loses mass. And meanwhile, the star continues pulling, orbit after orbit. There's a certain tragic elegance to the process. Not emotional tragedy exactly. The universe is not sentimental. but structurally the system resembles a slow unravelling. A planet pulled slightly beyond stability. One of the strangest consequences of tidal distortion is that the planet may no longer rotate independently in the way humans instinctively imagine worlds rotating. Because the planet is tidally locked, the same hemisphere always faces the star. Over time, gravitational interactions synchronized its rotation and orbit until the planet became permanently oriented toward the stellar source. That synchronization itself resulted from tidal forces. Long ago, the planet may have rotated more freely, but gravity gradually altered the rotation rate until equilibrium formed. This happens throughout the universe. Earth's moon became tidally locked the same way. Pluto and Charon are tidally locked to each other. Many exoplanets likely experience similar synchronization, but in most cases, tidal locking simply creates stable orientation. On WASP-12b, the forces involved are so extreme that the same process contributes directly to planetary deformation and destruction. The star essentially dominates the planet gravitationally. Another curious aspect of tidal stretching involves orbital decay. The tides raised inside both the star and planet do not remain perfectly aligned. Friction shifts them slightly. That misalignment transfers energy and angular momentum through the system. Over immense periods of time, those tiny energy exchanges accumulate, and in this case, astronomers suspect they are causing the orbit itself to shrink. The planet may slowly spiral inward toward the star. That detail transforms the entire system from unstable to actively doomed. Not immediately doomed, of course. Cosmic processes remain enormously patient, but the orbit appears to be evolving toward destruction rather than away from it. Every tidal interaction drains a little more orbital energy. Every orbit may pull the planet fractionally closer, and closer means stronger tidal forces, which means more stretching, more heating, more atmospheric loss. The system almost behaves like gravity discovering a feedback loop and becoming slightly too enthusiastic about it. Astronomers studying transit timings have found evidence supporting this possibility. Tiny shifts in the planet's orbital period suggest the orbit may indeed be decaying measurably. That is an extraordinary thing to observe. Planetary evolution usually unfolds far too slowly for humans to notice directly. Most orbital changes occur across billions of years, but WASP-12b may be extreme enough for modern astronomy to witness the process in action. We may actually be observing gravity dismantling a planet, and all of this inferred from distant starlight. There's something deeply impressive about that. Light travels over 1,400 years through interstellar darkness. Telescopes capture tiny fluctuations in brightness. Scientists analyze minute changes in timing and spectral signatures. From that information alone, humanity reconstructs the shape and fate of an alien world. A stretched planet larger than Jupiter slowly unravelling beside its star. Sometimes astronomy feels almost unfairly clever. One reason distorted planets fascinate researchers so much is because they help test theories about planetary interiors. The way a planet responds to tidal forces depends partly on its internal structure. Is the interior dense, fluid, layered, compressible? The stretching provides clues. In a sense, gravity performs experiments astronomers could never reproduce themselves. Scientists simply watch carefully enough to interpret the results. And the results here suggest a world under tremendous physical stress. At some point, the distinction between planet and material currently attempting to remain a planet becomes slightly blurry. There's also something psychologically strange about tidal distortion because humans instinctively think of planets as permanent solid things. Even though gas giants obviously lack surfaces in the traditional sense, we still imagine them as stable spheres hanging confidently in space. But the universe rarely guarantees perfect stability. Stars pulsate, galaxies collide, planets stretch, everything moves, everything changes. Even worlds larger than Jupiter can end up warped by gravity beyond comfortable limits. And yet despite all this violence, the system remains oddly orderly. The planet still follows a predictable orbit. The star still shines steadily. The gravitational equations still balance beautifully. Destruction in astronomy is often mathematically elegant. Which may sound unsettling, but there's also something strangely calming about it. The universe behaves consistently even during catastrophe. Gravity does not panic. Thermodynamics does not improvise. The same physical laws shaping peaceful planetary systems also shape doomed ones. Only the scale changes. Sometimes late at night, exoplanets like WASP-12b make Earth feel surprisingly gentle by comparison. Our oceans rise and fall quietly. Our orbit remains stable. Our planet stays comfortably spherical rather than gravitationally elongated. No star is currently pulling Earth apart layer by layer, which is reassuring news for everyone trying to sleep tonight. Although technically the Moon does continue stealing tiny amounts of Earth's rotational energy over time, so if you ever wanted evidence that the universe never completely stops interacting with itself, there it is. Everything gravitationally tugs on everything else eventually. Still, compared to WASP-12b, Earth lives an extraordinarily peaceful existence. This distant planet survives in conditions so extreme that gravity itself has become physically visible through deformation. The star pulls harder, the atmosphere stretches farther, the planet swells under heat, and slowly, steadily, the world begins losing the battle to remain whole. There is something deeply unsettling about the phrase, a star eating a planet. It sounds mythological somehow, like the sort of story ancient civilizations might invent after staring too long into firelight, a giant heavenly beast consuming worlds in the darkness above. But in the case of WASP-12b, the reality is stranger precisely because it is not dramatic in the way fiction usually prefers. The star is not swallowing the planet whole. There is no sudden collision, no explosion visible across the galaxy. Instead, the destruction is gradual, quiet, relentlessly patient. The star is feeding on the planet one layer at a time, and astronomers can actually see evidence of it happening. That remains one of the most astonishing parts of this entire story. Humanity has reached the point where we can detect a distant world slowly dissolving into its own star from over 1,400 light-years away. Not through imagination, not through artistic interpretation, through measurements, through light, through physics. The first clues emerged when astronomers began examining the atmosphere of WASP-12b more carefully using ultraviolet observations from the Hubble Space Telescope. Normally, when a planet passes in front of its star during a transit, it blocks a predictable amount of light depending on its size. But with WASP-12b, the planet appeared larger in ultraviolet wavelengths than expected. Much larger. That suggested something unusual surrounded the planet. An extended cloud of material, gas spreading outward far beyond the normal atmospheric boundary. The atmosphere was escaping. Hydrogen, helium, and other material were being stripped away into space by the combined effects of stellar radiation and gravity. And because the planet orbits so close to its star, the escaping gas does not simply drift away harmlessly into deep space. The star captures some of it, which means this entire system resembles a kind of cosmic siphon. The star pulls, the atmosphere stretches, gas escapes, the star absorbs it, again and again, orbit after orbit. There's something strangely intimate about the process. In most planetary systems, planets and stars remain distinct objects separated by enormous distances. Even Mercury, the closest planet to our Sun, stays safely tens of millions of kilometers away. But WASP-12b lives so dangerously close that the boundary between planet and star has begun breaking down. The planet is no longer fully self-contained. Part of it already belongs to the star. Astronomers believe the atmosphere may extend beyond the planet's Roche lobe. The critical gravitational boundary where the star's pull becomes stronger than the planet's ability to hold onto material. That is an incredibly dangerous place for a planet to exist. Imagine trying to carry water in a container that has already begun leaking from the sides. Now imagine the leak grows larger every orbit. That's roughly the situation here. The atmosphere continuously spills outward into space where stellar gravity can seize it. One of the reasons this process fascinates astronomers so much is because it reveals planetary destruction in real time. Usually, astronomical death happens on timescales far too vast for humans to witness directly. Stars evolve over billions of years, galaxies collide over immense epochs, even planetary formation unfolds slowly. But WASP-12b is extreme enough that modern telescopes may actually observe meaningful changes. We are not merely studying the aftermath of destruction. We are watching the process itself unfold. There's something quietly haunting about that. A distant world larger than Jupiter gradually unravelling, while human civilization briefly notices during one tiny slice of cosmic history. And the mechanism driving all this destruction is remarkably simple. Heat and gravity, that's all. No exotic physics required. The star bombards the planet with radiation so intense that the upper atmosphere heats dramatically. Hot gas expands outward. Once it expands far enough, stellar gravity begins pulling material away. The atmosphere effectively overflows. This process is sometimes compared to stellar winds or evaporation, although neither analogy fully captures the scale involved. We're talking about enormous quantities of gas escaping continuously from a giant planet. Astronomers estimate the planet may lose millions of tons of material every second. That number sounds catastrophic, and to be fair, it absolutely is. Yet the planet itself is so enormous that destruction still takes millions of years. That's one of the strange things about astronomy. The numbers become so large that even catastrophic loss can appear slow. A world can hemorrhage atmosphere continuously and still survive longer than human civilization has existed. Cosmic scales are difficult for the mind to hold comfortably. Another fascinating detail involves the shape of the escaping gas cloud itself. Observations suggest the material may form a kind of extended envelope or stream around the star-planet system, not unlike steam trailing from boiling water, or perhaps more accurately, like a comet tail generated by planetary destruction instead of icy sublimation. Except this tail originates from a giant gas world being gravitationally dismantled. There's an eerie beauty to the image. A dark, overheated planet racing around its star while trailing away pieces of itself into the surrounding system. And the star, meanwhile, remains largely indifferent. That may be one of the most emotionally strange aspects of astrophysics. The star is not actively attacking the planet. There is no intention involved. The star simply exists according to its own mass, radiation output, and gravity. The destruction happens automatically. Physics unfolds. Consequences follow. In many ways, the system resembles orbital inevitability rather than violence. And perhaps that's why it feels so mesmerizing late at night. The universe often behaves with enormous consistency, even during catastrophe. Stars do not rage. Gravity does not hesitate. Everything follows rules patiently and continuously, including destruction. Astronomers suspect that eventually WASP-12b may lose enough material that its structure changes dramatically. Some scientists believe hot Jupiters spiraling too close to stars might eventually become stripped-down remnants, exposing deeper planetary layers beneath their thick atmospheres. Others may simply disintegrate completely. In either case, the future appears bleak for this particular world, and the orbit itself may worsen the situation over time. Remember, evidence suggests the planet's orbit could be shrinking gradually through tidal interactions. If true, the planet is not merely close to its star, it is moving closer. Even tiny inward changes matter enormously, because gravitational and radiative effects increase rapidly with proximity. Closer means hotter. Closer means stronger tides. Closer means more atmospheric escape. which means the planet's destruction may accelerate gradually over time. The system almost behaves like a slow-motion spiral, a giant world trapped in a worsening cycle of heat, distortion, and mass loss. There's something surprisingly sobering about that idea. Humans often think of planets as stable, permanent things because our own world feels reliable on everyday timescales. Mountains stay where they are. Oceans remain in place. The sun rises predictably. But planetary stability is not guaranteed everywhere. Some worlds exist under temporary conditions. Some survive only because of delicate balances. And some, like WASP-12b, wander too close to danger and begin coming apart. Exoplanet discoveries have repeatedly reminded astronomers that our solar system may actually be unusually calm. Hot Jupiters alone were a major shock when first discovered. Before the 1990s, many scientists assumed giant gas planets would naturally remain far from stars because that's what Jupiter and Saturn do. Then suddenly, astronomers found enormous worlds orbiting blisteringly close to their stars all across the galaxy. The universe turned out to be far more chaotic than expected. And among those hot Jupiters, WASP-12b became one of the most extreme examples because it appears to have crossed from merely hot into actively unstable territory. It is no longer simply existing near danger. It is being consumed by it. One particularly interesting consequence of atmospheric loss is how it changes the planet's observable properties over time. The atmosphere influences temperature distribution, density, reflectivity, and spectral signatures. As material escapes, those characteristics evolve. In principle, astronomers observing the system across sufficiently long timescales might detect the planet physically changing. That possibility still feels extraordinary. Human beings evolved without even knowing other planetary systems existed. Now we monitor the atmospheric erosion of distant worlds. Science sometimes advances so quickly, it becomes difficult emotionally to catch up with it. Another curious aspect of this process is how much it resembles phenomena normally associated with stars rather than planets. In close binary star systems, one star can pull material away from another through Roche-Lobe overflow. Matter streams from one star toward its companion, forming accretion structures and complex gravitational interactions. WASP-12b behaves almost like a miniature planetary version of that process. The star and planet have become gravitationally entangled beyond ordinary planetary relationships, which makes the system feel oddly transitional. Not fully a normal planetary system anymore, not quite a binary stellar system either. Something in between. Astronomy loves in-between states. Objects caught mid-transformation often become the most scientifically valuable because they reveal processes normally hidden by stability. A star forming, a galaxy colliding, a black hole feeding, a planet evaporating. Moments of change teach astronomers more than moments of equilibrium, and this system is all change, heat escaping, gas flowing, gravity distorting, orbital energy draining, everything evolving continuously. Sometimes late at night there's something almost calming about realizing the universe is never truly static. Even seemingly permanent objects are constantly shifting. Stars burn fuel, continents drift, galaxies rotate, planets migrate. Change is not an interruption of the cosmos, it is the cosmos. Still, few places illustrate that more dramatically than WASP-12b, a giant world larger than Jupiter gradually dissolving into its own star under relentless heat and gravity. And yet, despite the violence of the environment, there's another strange question scientists began asking once they understood the planet better. If a world like this somehow had an observer floating above it, what would the actual experience look like? What would the skies resemble? What colours would appear? What would the atmosphere itself feel like in a place where an entire planet is slowly being pulled apart? Picture the atmosphere of a planet so hot that the usual boundaries between sky, weather and fire begin to lose their meaning. Not because the planet is literally covered in oceans the way Earth is covered in water, but because the temperatures are high enough for rock, metal and chemistry itself to behave in ways that feel almost impossible from the comfort of a quiet room on Earth. On our world, lava is something that erupts from below. It spills from volcanoes, glows orange in the dark, cools into black stone, and becomes part of the ground again. On a world like WASP-12b, heat is not a rare event rising from cracks in a crust. Heat is the condition of existence. It is the rule. It is the weather, the pressure, the light, and the background to everything. Now, to be careful, WASP-12b is not a rocky planet with literal oceans in the Earth-like sense. It is a gas giant, more like Jupiter than Earth, so it probably does not have a solid surface where molten rock could pool beneath a sky. But the phrase oceans of lava captures something important about the environment around this planet, because on worlds this hot, materials that would be solid or liquid on Earth can become vapor, haze, cloud, or part of the atmosphere itself. Rock-forming elements, metals and exotic compounds can be lifted into skies where temperatures would make ordinary geology surrender immediately. A mountain on Earth may melt in a furnace. Around WASP-12b, the furnace is the planet. That is a strange thought to settle into gently. A world where the familiar categories we use on Earth stop working. Ground, sky, ocean, weather, surface, cloud. These words were made by creatures who evolved on a moderate rocky planet with rain, breathable air and temperatures that usually allow furniture to remain solid. We carry those words into space and try to use them elsewhere, but sometimes the universe politely takes them apart and hands them back with a note saying, "Not quite." WASP-12b is one of those places. On Earth, the sky is a thin blue shell that protects us. It scatters sunlight, carries clouds, moves storms, and lets birds and airplanes cross through it. It can feel dramatic during thunder or peaceful during sunset, but it remains familiar. Even when weather is dangerous, the atmosphere behaves within a range our species understands. We know what rain is, we know what wind is, we know what heat feels like when summer refuses to be reasonable. We may complain, and rightly so, but at least the air is not glowing because it has been heated to thousands of degrees. On WASP-12b, the dayside atmosphere is blasted by its star continuously. Because the planet is probably tidally locked, the same side faces the star at all times. There is no ordinary sunrise, no evening relief, no gentle golden hour where the light softens and everyone briefly considers becoming a photographer. The star hangs in the same region of the sky, pouring radiation into the atmosphere without pause. The result is a planetary climate system pushed into extremes that make Earth's weather feel almost domestic. Temperatures on the day side reach roughly 2,500 degrees Celsius or more. At those temperatures, many molecules cannot survive intact for long. Water vapor can break apart. Some compounds dissociate into atoms. Metals can exist as vapor. Clouds, if they form at all, are not fluffy white shapes drifting lazily above a meadow. They may involve materials that on Earth belong inside rocks, furnaces, or industrial processes. Imagine a sky where the ingredients of stone are not safely beneath your feet, but part of the air itself. It is not the sort of forecast anyone would want to read calmly over breakfast, and still we can explain it. That may be one of the most comforting things about even the strangest astronomy. The place can be wild beyond imagination, but it is not beyond reason. Heat breaks molecules, gravity pulls gas, radiation transfers energy, winds move from hot regions toward cooler ones. The rules remain steady, even when the outcome is astonishing. The day side of WASP-12b receives so much energy that its upper atmosphere becomes a restless, expanding layer. Gas heats, expands, and tries to escape. On a cooler planet, gravity might keep the atmosphere tightly held, but this world is swollen by heat and stretched by tides, so its upper layers reach outward like steam rising from something that has been left on the stove much too long. and unlike a pot on a stove, there is no one nearby to turn the burner down. That constant heating creates enormous pressure differences between the permanent day side and the permanent night side. One hemisphere is roasted continuously while the other faces space. You might expect the night side to be cold by comparison, and in a relative sense it is cooler. But cooler here is doing heroic work. The atmosphere transports heat around the planet through powerful winds. Air heated on the day side rushes toward the night side, carrying energy across the globe at incredible speeds. These winds may move at kilometers per second, faster than sound under many conditions, and they do not blow across landscapes or oceans the way winds do here. They race through layers of gas wrapped around a giant planet that has no solid surface to slow them, so the sky never rests. It does not drift lazily from calm to breeze to storm. It circulates under relentless forcing, driven by one side receiving constant stellar punishment, and the other side trying to radiate heat away into space. The atmosphere becomes a conveyor belt of heat, chemistry, and motion. It is not weather as we know it. It is a global energy redistribution system with winds so extreme that a hurricane on Earth would seem like a polite cough beside it. There is a quiet wonder in that, even if the environment itself is terrifying. A planet can become a machine for moving heat. Its atmosphere can behave like a vast engine, powered by starlight, shaped by rotation, gravity, and pressure. We often think of planets as places, but in astronomy they are also processes. They are not just objects sitting there. They are systems constantly responding to energy. Earth responds gently enough for life. WASP-12b responds by boiling, swelling, darkening, and shedding itself into space. One of the more unusual features of WASP-12b is how dark it appears in visible light. You might expect a planet so close to its star to shine brightly from reflected starlight, like Venus shining in our evening sky. But observations suggest WASP-12b reflects very little of the visible light that falls on it. Its atmosphere absorbs much of that radiation rather than scattering it back. So imagine, if you can, a planet nearly black in reflected light, yet intensely hot. Not bright like polished ice, not pale like Jupiter's cloud bands. Dark, swollen and glowing mostly because of heat. It is a furnace-coloured world rather than a mirror. A planet that takes in starlight and keeps it, as though the atmosphere itself has learned the unfortunate habit of holding on to everything. That darkness likely comes from the extreme temperatures preventing reflective clouds from forming normally. On cooler gas giants, clouds can scatter light and make planets appear brighter. But WASP-12b is too hot for many of those reflective cloud particles to remain stable on the day side. Instead, the atmosphere absorbs incoming light deeply, turning stellar energy into heat. In some wavelengths, it may glow from thermal emission. In others, it appears almost lightless. This gives the planet a strangely unsettling character. It is close to a star, flooded by radiation, and yet visually dark. A blackened world near fire. Not cold darkness, but overheated darkness. Like a coal glowing from within after the flame has passed over it. On the night side, conditions may allow different chemistry to occur. As gas flows away from the day side and cools, some compounds may recombine. Clouds might form in colder regions, possibly made from exotic materials. Then winds may carry those gases back toward the day side, where intense heat breaks them apart again. The atmosphere could be constantly cycling between forms, molecules assembling and disassembling, vapors condensing and evaporating, heat tearing apart what cooler regions briefly create. That kind of cycle is difficult to imagine because Earth's chemistry feels stable by comparison. Water evaporates, condenses, falls as rain, gathers in rivers, and returns to the sea. We call that the water cycle, and it is one of the quiet engines of life. On extreme hot Jupiters, the cycles may involve materials far less cozy. Instead of rainwater, there may be chemical patterns involving vaporized metals, dissociated molecules, and clouds made from substances that would be minerals on Earth. Not exactly weather for an umbrella, although to be fair, an umbrella would last approximately no time at all. The deeper atmosphere would be stranger still. Gas giants do not offer a clear landing place. If you descended into Jupiter, you would move through layers of gas growing denser and hotter until the distinction between atmosphere and interior gradually blurred. On WASP-12b, extreme external heating complicates that structure further. The upper layers are inflated, escaping, and battered by radiation. Lower regions are under greater pressure. Somewhere deep inside, hydrogen may behave in exotic ways under compression. The planet may have a core, perhaps made of heavier elements, buried under immense layers of gas, but there is no gentle solid shoreline between air and ground, no beach, no cliff, no peaceful place to stand and observe the terrible sky. Science fiction often imagines alien planets as alternate landscapes, blue deserts, purple forests, seas under strange moons. But many real exoplanets are not landscapes at all. They're enormous physical environments without surfaces, without horizons humans could use normally, without breathable air or solid ground. WASP-12b reminds us that not every planet is a place in the human sense. Some are worlds of pressure, heat, and fluid motion. And yet, they are planets all the same. That thought expands the word. A planet does not have to be a comfortable ball of rock. It can be a swollen gas giant being stripped by its star. It can be dark as charcoal in visible light, hotter than lava, shaped like an egg, and losing atmosphere into space. The universe gives categories very wide boundaries. The sky of WASP-12b would also be shaped by the enormous apparent size of its star. From Earth, the Sun appears as a small disk. Bright, yes, but small enough that we can block it with a thumb at arm's length, which is a lovely fact and also a terrible idea to test directly with your eyes. From WASP-12b, the parent star would loom much larger because the planet orbits so close. The star would fill a significant portion of the sky, dominating the dayside view completely. There would be no gentle celestial backdrop, no familiar blue dome with a small sun moving across it. The star would appear huge, fixed, and overwhelming, pouring light into an atmosphere already stretched near its limits. If the planet's atmosphere were visible from within, it might shimmer, glow, and churn under the heat. The entire sky could feel like the inside of a furnace window. On the night side, the view would not necessarily be peaceful either. The atmosphere may remain hot enough to glow. Winds from the day side would carry heat around. Chemical hazes and clouds could obscure the sky. And because the planet orbits so close, tidal forces would keep everything locked into a rhythm that never resembles Earth's day-night cycle. The night side would not be a calm winter night under stars. It would be the dark side of an overheated giant world, wrapped in rushing gas, permanently turned away from the star but never fully free from it. The boundary between day and night, called the terminator, may be especially dynamic. On Earth, the terminator is simply the moving line of sunrise or sunset sweeping across the globe. It passes over oceans, mountains, cities, forests, and sleeping cats who object to the changing light with great seriousness. On WASP-12b, because the planet is tidally locked, the terminator stays roughly fixed. It is the permanent twilight belt between the star-facing hemisphere and the night-facing hemisphere. But that does not mean it is calm. It may be a region of fierce winds, steep temperature gradients, and complex chemistry, where gas heated on the day side rushes toward darker longitudes and begins changing form. If there were any place on such a planet where conditions might be slightly less extreme, it would be somewhere near this transition zone. But less extreme still means utterly hostile. This is not a twilight zone of habitability. It is simply the portion of a planetary furnace where the furnace is slightly less direct. What makes WASP-12b especially useful scientifically is that its atmosphere is not hidden from us completely. Because the planet transits its star, astronomers can study changes in starlight during those passages. When the planet moves in front of the star, some light filters through its atmosphere. That light carries clues. Different wavelengths are absorbed by different atoms and molecules. By carefully studying the star's spectrum during transit, scientists can infer what the atmosphere contains and how far it extends. Then, when the planet passes behind the star, astronomers can measure the combined light before and after its disappearance. This helps estimate how much light and heat the planet itself contributes. These measurements are delicate, almost absurdly delicate. It is like trying to understand a candle flame by watching how a lighthouse changes when a moth passes nearby. And still, the technique works. From far away, across more than 1,000 light-years, we learn about a sky that never rests. There is something deeply soothing about that patience. Telescopes collect photons. Scientists compare curves. Years of measurements become evidence. A distant world takes shape not through direct touch, but through careful attention. Astronomy is often the art of noticing extremely small changes and taking them seriously. And WASP-12b rewards attention because it is so extreme. Its atmosphere is inflated, its orbit is short, its star is bright enough for useful observations, its transits repeat often. Every 26 hours the planet gives astronomers another chance to watch it pass before its star. Another chance to measure the tiny dimming, another chance to refine models of heat, chemistry and escape. The planet's atmosphere also tells a story of imbalance. On Earth, life depends on balance. Too much heat and water evaporates. Too little and oceans freeze. Too much atmosphere and greenhouse warming becomes severe. Too little and pressure drops away. Earth's systems are not perfectly stable forever, but they operate within a range where life can adapt. WASP-12b is what happens when balance fails in nearly every direction. It is too close, too hot, too distorted, too irradiated, too inflated to hold on to itself securely. And yet it persists, at least for now. That, for now, matters. The planet is not gone. It has not yet merged with the star. It continues orbiting, its atmosphere continues circulating, its material continues escaping. The world remains in a temporary state between survival and destruction, not whole in the comfortable sense, but not vanished either. Maybe that is why the image lingers. A planet can be in the process of ending for millions of years. It can look stable from one orbit to the next while changing slowly over time. It can keep circling, glowing, losing mass, and darkening under stellar heat. The universe does not always separate existence and destruction neatly. Sometimes they overlap. The idea of lava also helps us remember how far beyond Earth's conditions this world sits. On Earth, lava is rare enough to draw crowds from a safe distance. People watch volcanic flows with awe, because molten rock reveals the planet's inner heat. It is Earth briefly showing its deep engine at the surface. But on ultra-hot worlds, the temperatures associated with lava are not exceptional. They're ordinary environmental conditions. What melts rock here may simply be part of the atmospheric baseline there. So when we imagine oceans of lava around WASP-12b, we're really imagining a broader truth. This is a planet where the heat normally hidden inside worlds has become an atmospheric condition. Not a surface event, not a temporary eruption, but a global state driven by closeness to a star. It is not geological fire coming up from below. It is stellar fire pressing down from above. And the sky never rests because the energy never stops arriving. There is no nightfall on the day side to soften it, no seasonal winter to cool it, no clouds bright enough to reflect most of the light away, no safe distance. The planet receives, absorbs, circulates, loses and receives again. The whole atmosphere becomes a restless exchange between star and space. The star gives radiation. The planet absorbs heat. The winds move energy. The atmosphere expands. Gas escapes. The star pulls that gas away. Round and round the system goes, each orbit so short that years pass almost like breaths. Compared with this, Earth's atmosphere feels wonderfully quiet. Even when storms gather, even when winds howl, even when summer heat presses heavily against windows, our sky remains gentle by cosmic standards. It rains water here. Clouds are made of tiny droplets or ice crystals. Winds move through air we can breathe. The sun rises and sets at a distance that permits morning coffee rather than atmospheric vaporization. We live under a sky that, most days, is kind enough to be ordinary. That ordinariness is easy to overlook. Extreme exoplanets give it back to us. They show us what planets can be when pushed beyond comfort. They widen the range of possible worlds until Earth appears not boring, but astonishingly moderate. A place where chemistry is calm enough for cells. Where rocks remain solid underfoot. Where the sky changes colour without becoming a furnace. Where night arrives every evening and gives the planet time to cool. On WASP-12b, there is no such kindness. The planet is trapped in closeness, its atmosphere moving endlessly between light and dark, its chemistry breaking and reforming, its upper layers escaping into the surrounding system. It is not a landscape of lava seas in the way a rocky super-Earth might be. It is something stranger, a gas giant so hot that lava-like temperatures define the air itself. That distinction matters because it makes the planet even more alien. A molten rocky world is extreme, but at least it has a surface. WASP-12b is a world without a normal surface, with heat severe enough to erase familiar boundaries. It is a planet where the idea of standing, sailing, breathing, or watching clouds becomes impossible. You cannot visit it in imagination without rewriting the meaning of visit. You would not stand on WASP-12b. You would fall into it. You would not breathe its air. Its air would destroy anything human long before breathing became relevant. You would not watch the weather. You would be inside a global storm of heat, pressure, radiation, and escaping gas. And yet, as a thing to understand, it is beautiful in the way scientific clarity can be beautiful. Every extreme feature connects to another. The close orbit causes intense heating. The heating inflates the atmosphere. The tidal forces stretch the planet. The stretched atmosphere escapes more easily. The escaping gas reveals itself in transit observations. The planet's darkness tells us about missing reflective clouds and strong absorption. The winds tell us about heat redistribution. The short year gives repeated opportunities to study the whole system again and again. Nothing is isolated. Everything belongs to the same story. That story is not finished because WASP-12b is still changing. Its orbit may continue shrinking, its atmosphere may continue thinning, its star may continue drawing material away. In the distant future, the planet may be destroyed entirely, swallowed or torn apart, leaving behind only traces in the star's outer layers, or perhaps a remnant core if one survives long enough. But for now, it remains visible to us through the methods of modern astronomy. A dark giant near its star, a planet hotter than lava, a sky that never rests. Suppose, for just a moment, that impossibility stopped mattering. Suppose you could somehow float safely above WASP-12b without burning, without being crushed, without instantly becoming part of a physics lesson titled, "Why Humans Should Stay on Earth." Imagine you had some miraculous protective vessel, something capable of resisting temperatures hotter than lava, winds moving faster than sound, and radiation intense enough to rip ordinary molecules apart. What would it actually feel like to be there? That question may sound simple, but it reveals something fascinating about how humans understand planets. We do not naturally think in equations or orbital mechanics. We think through experience, through sensation, through sight, sound, scale, movement, temperature. We imagine standing somewhere because standing somewhere is how our species learned to understand the world in the first place. So even though WASP-12b is not a place you could truly stand, imagining the experience helps translate astronomy into something almost personal. The first thing you would notice is the star, not eventually, immediately. It would dominate everything. From Earth, the sun looks relatively small in the sky despite being enormous, because it is safely distant. You can hold a thumb at arm's length and cover it completely. That comforting little trick only works because Earth stays about 150 million kilometers away. But WASP-12b orbits terrifyingly close to its star, close. The star would loom overhead like an enormous blazing wall of light. It would not feel like sunshine in the earthly sense. There would be no pleasant warmth on your skin, no bright afternoon sky, no golden glow slipping through clouds. The star would feel oppressive, violently bright, the sort of brightness that stops feeling like illumination and starts feeling like exposure. Even through heavy shielding, you would instinctively understand that this is not a place where living things belong. And because the planet is probably tidally locked, the star would not move across the sky. It would simply remain there, hanging over the same hemisphere forever. No sunrise, no sunset, no evening cooling, just endless stellar presence. Humans are deeply tied to cycles of light and darkness. Morning wakes us, night calms us. Our bodies evolved around rotation. Even artificial lighting cannot fully erase that ancient biological rhythm. But on WASP-12b, one side of the planet never escapes the day. That alone would feel psychologically strange. The sky itself would likely appear unlike anything humans instinctively recognize. Earth's atmosphere scatters blue wavelengths of sunlight, giving us familiar blue skies during the day and reds and oranges near sunset. Those colours come from a relatively cool atmosphere under moderate stellar radiation. Here, the atmosphere is heated to extraordinary temperatures. Molecules break apart. Exotic chemistry dominates. Clouds, if present, may consist of strange mineral compounds or vaporized materials impossible under Earth conditions. The sky might glow with deep orange or reddish tones from thermal radiation. Certain regions may shimmer through dense haze. Other wavelengths invisible to human eyes would flood the atmosphere constantly. And perhaps strangest of all, the atmosphere itself would not feel stable. On Earth, air usually behaves politely enough for us to ignore it most of the time. It drifts softly through trees. It carries weather systems gradually across continents. Even during storms, there are pauses, moments of stillness between gusts. WASP-12b has no such patience. The atmosphere is in constant violent motion because the day side absorbs enormous amounts of heat continuously, while the night side radiates energy away into space. That imbalance drives winds at astonishing speeds, several kilometers per second, fast enough that ordinary human comparisons stop working comfortably. Earth hurricanes can reach roughly 250 kilometers per hour during extreme events. Those storms flatten buildings and uproot trees. On WASP-12b, atmospheric circulation may move many times faster than that. Not occasional storms. The entire atmosphere itself becomes a permanent storm system. If you somehow floated above the cloud layers in a protected observation craft, you might see vast streams of glowing gas racing across the planet from the day side toward the night side. Immense atmospheric currents carrying heat around the globe endlessly. There would be no quiet weather, no calm afternoon, no peaceful clearing after rain. The sky never rests because the energy imbalance never rests. And then there is the heat. Humans are surprisingly fragile creatures when it comes to temperature. A few degrees above normal body temperature can become dangerous. A hot summer afternoon sends entire populations searching desperately for shade and refrigerated drinks. Many of us begin behaving emotionally toward air conditioning somewhere around 30 degrees Celsius. WASP-12b reaches over 2,500 degrees. At those temperatures, the distinction between hot and structurally alarming disappears. Your protective vessel would need to shield you not only from thermal radiation, but from an environment capable of vaporizing many ordinary materials entirely. Even metals we think of as sturdy would soften or melt. The atmosphere itself would glow with heat. There is something deeply unsettling about imagining air hot enough to shine. On Earth, glowing usually belongs to fire, lava, or heated metal. But here, entire atmospheric regions approach those conditions continuously. And because the planet is a gas giant, there is no comfortable solid ground waiting below. This is important because humans instinctively imagine standing on planets the way we stand on Earth. We picture landscapes, horizons, cliffs, valleys. Gas giants do not work that way. If you descended downward through the atmosphere, you would simply move through thicker and denser gas layers. Pressure would rise steadily, temperatures would increase further, winds would continue raging around you. Eventually conditions would become crushing beyond comprehension. There is no beach, no mountain, no volcanic plain, no stable place where boots could touch the ground. Instead, the planet becomes a gradual transition from atmosphere into deeper atmosphere into compressed planetary interior. You would not stand there, you would sink, forever, or at least until pressure and temperature ended the experiment very decisively. That alone makes the planet feel alien in a profound way. Humans evolved on surfaces. We think in terms of walking, climbing, sitting, building. A world without solid ground challenges something very old in the human imagination. Even oceans on Earth eventually led downward to sea floor. Gas giants do not offer that reassurance. And yet, despite lacking a surface, the planet still possesses gravity comparable to, or stronger than Earth's, depending on altitude. You would feel pulled downward continuously toward deeper atmospheric layers. Combined with the winds and heat, the entire environment would feel less like visiting a world and more like being trapped inside a planetary engine. The sound would likely be extraordinary too. Of course, real sound transmission depends on atmospheric density and composition, but assuming your craft could translate the environment into audible experience safely, you might hear enormous roaring atmospheric motion constantly. Deep thunder-like turbulence, supersonic winds, immense pressure waves. Earth storms sometimes sound frightening because they briefly remind us how small we are beside nature. A strong thunderstorm rattling windows at night can still make humans pause instinctively. Now imagine a planet where the storm never ends, a permanent atmospheric violence spanning an entire world. Another strange feature would involve the apparent speed of time itself, not literal time dilation in the relativistic sense, though technically tiny relativistic effects always exist. More the psychological sensation created by the incredibly short year. Remember, WASP-12b completes an orbit in about 26 hours. An entire year passes almost as quickly as an Earth day. If humans somehow lived in such a system long enough to adapt psychologically, calendars would become surreal by earthly standards. Birthdays every few days, thousands of local years passing across one human lifetime. Seasonal thinking would vanish entirely because there are no meaningful Earth-like seasons in such an orbit. Astronomy often reminds us that many concepts humans treat as universal are really local habits. A year is not universal. Sunrise is not universal. Even weather itself is not universal. WASP-12b feels so strange partly because it dismantles many assumptions humans unconsciously carry about what planets should be. One especially haunting aspect of the experience would probably be the awareness of ongoing destruction. Because unlike many planets that merely exist under extreme conditions, WASP-12b is actively losing itself. The atmosphere is escaping into space. The star is pulling material away continuously. If your observation systems could detect ultraviolet glow or extended atmospheric structures, you might actually see streams of gas escaping outward. a planetary atmosphere bleeding into surrounding space. There's something deeply eerie about that image. Not sudden destruction, slow destruction, the kind the universe specializes in. Humans are emotionally prepared for explosions because explosions are fast and dramatic. But gradual unraveling feels stranger somehow. More difficult to process emotionally because it unfolds continuously without climax. WASP-12b is not dying in a single moment. It is dying orbit by orbit, and that process may continue for millions of years. One detail scientists find especially fascinating is how dark the planet appears in visible light despite its extreme heat. If you looked directly at the planet, it might not appear brilliantly reflective like clouds on Jupiter or Venus. Instead, the atmosphere absorbs much of the incoming light. So imagine a giant dark world glowing faintly red from heat, while orbiting close to a blazing star. A planet blackened by radiation, like charcoal held near a furnace. That visual contrast would likely feel unforgettable. The star glaring with overwhelming brilliance, while the planet itself remains strangely dark beneath the heat. And somewhere around you, always, would be the awareness of scale. Humans are not naturally equipped to emotionally process planetary scales comfortably. Spacecraft windows showing entire atmospheric systems curving across horizons would constantly remind you that this is not weather over a city or ocean. This is a whole planet behaving violently, a world larger than Jupiter stretched by gravity, blasted by radiation, and slowly consumed by its star. Even the night side, if you travelled there, would not provide peace in the earthly sense. Yes, the direct stellar radiation would disappear beyond the terminator, but the atmosphere would remain hot. Winds from the day side would continue transporting energy. The sky might glow dimly from thermal radiation or scattered atmospheric effects. And overhead, perhaps, you would see the star hidden just beyond the horizon, its influence still shaping everything despite its absence from direct view. The transition region between day and night might be especially dramatic, a permanent twilight zone where supersonic winds carry heated gas away from the star-facing hemisphere while cooler material circulates back. Not peaceful twilight, more like the edge of a gigantic atmospheric machine. There is something oddly fascinating about how completely unlivable some planets become while still remaining scientifically beautiful. WASP-12b is not beautiful because it is safe. It is beautiful because physics reveals itself there so clearly. Heat, gravity, radiation, atmospheric dynamics, orbital mechanics, everything stripped down to extremes. The universe often becomes easiest to understand in places least suitable for living, and perhaps that's part of why humans find worlds like this so compelling late at night. Extreme exoplanets stretch imagination beyond ordinary experience. They remind us that Earth represents only one version of what a planet can be, a remarkably gentle version, as it turns out. Compared to WASP-12b, Earth feels astonishingly calm. Our skies change gradually. Our storms end eventually. Our atmosphere remains cool enough for rain instead of vaporized minerals. Our world stays comfortably distant from the sun. Even volcanic eruptions, terrifying as they can be locally, are tiny compared to the continuous planetary scale heating happening on this distant giant. Exoplanets often make Earth feel less ordinary rather than less important. A stable orbit begins looking precious. A breathable atmosphere begins feeling miraculous. The simple existence of shade suddenly seems luxurious. And maybe that is one of the quiet gifts astronomy offers. It does not merely show us strange, distant worlds. It changes how we see our own. Long before astronomers discovered planets around other stars, our own solar system quietly trained us to expect a certain kind of order. Small rocky planets close to the sun, giant gas worlds farther away, wide stable orbits lasting billions of years, everything arranged with enough neatness that textbooks could draw tidy diagrams, and school children could memorize them without developing existential concerns before lunch. Then exoplanets arrived and immediately behaved like they had never seen the textbook. Among the biggest surprises were hot Jupiters, enormous gas giants orbiting absurdly close to their stars, worlds larger than Jupiter completing entire years in days instead of decades. At first, astronomers genuinely struggled to explain them because according to standard planetary formation theories, giant gas planets should not form in such scorching environments. Gas giants require large amounts of material, ice, gas, dust, and heavier elements all accumulating gradually in colder outer regions of young planetary systems. Beyond what astronomers call the frost line, temperatures become low enough for volatile compounds like water and methane to freeze into solid grains. Those icy materials help planetary cores grow rapidly enough to capture huge gas envelopes before the young star blows remaining material away. That process works beautifully for Jupiter and Saturn. But near a star, too hot, too chaotic, too much radiation. The inner regions of young systems generally lack the conditions needed to build giant gas planets comfortably, which means hot Jupiters probably were not born where we find them now. They moved. And that realization changed planetary science profoundly, because once astronomers accepted planetary migration as a real process, solar systems stopped looking like permanent structures and started looking more like evolving gravitational ecosystems. Worlds shift, orbits change, gravity rearranges entire systems over time. Some planets survive migration safely, others do not. And WASP-12b may represent one of the final stages of what happens when migration goes too far. A giant world trapped in a slow death spiral toward its star. There's something quietly unsettling about the phrase death spiral because it suggests inevitability rather than catastrophe. Not a sudden collision, not an explosion, just a gradual inward drift that becomes harder and harder to escape. And in astrophysics, gradual processes often become the most powerful ones because the universe is extraordinarily patient. A planet does not need to fall quickly to be doomed. It only needs to fall continuously. Astronomers believe many hot Jupiters probably formed far from their stars before migrating inward early in their system's history. One leading idea involves interactions between young planets and the thick disks of gas and dust surrounding newly formed stars. Young planetary systems are messy places. Before planets settle into stable configurations, enormous amounts of gas swirl around the star in a rotating disk. Embedded within that disk, growing planets gravitationally disturb the surrounding material. Those disturbances create torques, tiny gravitational imbalances that can slowly alter planetary orbits, sometimes outward, often inward. Imagine trying to move through thick water while currents continuously tug at you. Over time, even small forces change your path. Planets migrating through young disks experience something similar. And giant planets like WASP-12b may have slowly spiraled inward over hundreds of thousands or millions of years until they reach dangerously close orbits. Another possible mechanism involves gravitational chaos between planets themselves. Young systems may originally contain multiple giant planets interacting gravitationally. Those interactions can destabilize orbits dramatically. One planet may get thrown outward into deep space, another may plunge inward toward the star. Solar systems, it turns out, can occasionally behave less like elegant clockwork and more like a crowded room where gravity keeps bumping into furniture. In some simulations, giant planets end up on highly elongated orbits before tidal interactions with the star gradually circularize the orbit closer in. That's important because tidal interactions become increasingly powerful at close distances, and this is where the strange death spiral truly begins. Once a giant planet settles into an extremely close orbit, the relationship between planet and star changes fundamentally. The star's gravity raises tides inside the planet. The planet raises tides inside the star. Those tidal bulges do not remain perfectly aligned because real physical objects experience friction internally. Gas moves, energy dissipates, rotating material lags slightly behind gravitational forcing. That misalignment transfers angular momentum between the two bodies, and over immense periods of time, orbital energy can slowly drain away. The planet spirals inward, not dramatically, not visibly from orbit to orbit, but steadily. The process resembles a skater gradually losing momentum while circling inward on ice. Each pass around the star costs a tiny amount of orbital energy, and for planets already orbiting extremely close, even tiny changes matter enormously. Closer means stronger gravity. Closer means more tidal distortion. Closer means more heating. Closer means more atmospheric escape. Everything intensifies. That is the terrifying efficiency of feedback loops in astrophysics. Once certain thresholds are crossed, processes begin amplifying one another. For WASP-12b, the inward drift likely increases the tidal stress, which increases internal heating, which inflates the atmosphere, which makes atmospheric escape easier, while the orbit itself may continue shrinking. A world gradually pulled beyond stability. There's something oddly emotional about hot Jupiters, even though planets themselves feel nothing. Perhaps because the process resembles exhaustion structurally. The closer the planet moves toward the star, the harder it becomes for the planet to remain intact. And unlike ordinary planetary evolution, this process may unfold on comparatively short astronomical timescales, millions rather than billions of years. That's still vastly longer than human civilization, of course. Humans become impressively relaxed about deadlines once the numbers exceed several 100,000 years. But cosmically speaking, a few million years can be relatively brief. Earth has existed for about 4.5 billion years. The Sun will survive several billion more. Compared to stable planetary lifetimes, WASP-12b appears temporary, a giant planet trapped in an unstable phase. One fascinating question astronomers began asking after discovering hot Jupiters was why our own solar system lacks one. Why doesn't Jupiter orbit close to the Sun? Why did our planetary architecture remain comparatively orderly? The answer may involve migration histories. Jupiter likely migrated somewhat early in solar system history, but interactions with Saturn may have prevented catastrophic inward movement. Some models suggest Jupiter actually moved inward partially before reversing direction outward again. That possibility is astonishing when you pause to consider it. The solar system itself may once have looked dramatically different. Planetary systems are not frozen arrangements handed down permanently from creation. They evolve dynamically. Gravity reshapes them continuously. Earth's calm orbit may partly reflect fortunate circumstances rather than inevitability. Exoplanets have repeatedly taught astronomers this lesson. The universe does not guarantee stable, habitable worlds. Some systems become chaotic. Some planets collide. Some are ejected into interstellar darkness, and some giant worlds spiral inward toward destruction. The strange thing is that hot Jupiters were once thought impossible largely because scientists unconsciously assumed our solar system represented a typical arrangement. Then the galaxy politely disagreed. One of the reasons hot Jupiters were discovered so early in exoplanet research is precisely because they orbit so close to their stars. Large planets block noticeable amounts of starlight during transits. Their short orbital periods create frequent detectable events. Their gravity also produces measurable stellar wobbles. In a way, these worlds announce themselves loudly. The galaxy introduced itself through extremes first, and among those extremes, WASP-12b became one of the most dramatic because it may actually be nearing the final stages of close orbit evolution. Astronomers studying transit timings have detected evidence suggesting the orbital period may be decreasing gradually. That detail is extraordinary. Planetary orbits normally appear perfectly stable on human timescales. Detecting measurable orbital decay within modern astronomy itself is rare because celestial mechanics usually unfold too slowly for humans to notice directly. But this planet may be extreme enough for the process to reveal itself. Tiny shifts in timing accumulate. The planet arrives slightly earlier than expected. The orbit shrinks imperceptibly. And from those tiny measurements, astronomers infer something astonishing. The spiral inward has already begun. That realization transforms the system from merely dangerous into terminal. Again, not terminal tomorrow morning. Cosmic destruction prefers patience, but terminal nonetheless. There's something deeply eerie about watching orbital mechanics become destiny. Gravity does not rush, it simply continues. One especially interesting aspect of hot Jupiter death spirals is what eventually happens to the planets themselves. Several possible endings exist. In some scenarios, the atmosphere gradually strips away until only a dense core remains. The giant gas envelope disappears entirely, leaving behind a smaller remnant world orbiting extremely close to the star. In others, tidal forces eventually tear the planet apart completely, and in the most dramatic cases, the planet may spiral directly into the star itself. Astronomers suspect stars can actually consume planets occasionally during their lifetimes. When that happens, the star may brighten temporarily, or show unusual chemical signatures in its outer layers. Some stars may carry evidence of ancient planetary meals. That is a wonderfully unsettling sentence. The universe contains stars that may have eaten their own worlds. And perhaps somewhere in the galaxy tonight, another hot Jupiter is already nearing its final inward plunge. One strange consequence of studying exoplanets is realizing how temporary planetary systems can be. Humans instinctively think of planets as permanent because Earth feels ancient and stable. But stability is conditional. Everything depends on orbital distance, gravitational interactions, stellar evolution, and timing. Move a giant planet too close to a star, and eventually the system begins unraveling. Sometimes slowly enough that the process looks almost calm. That calmness may be the most haunting part. If you observed WASP-12b from far away, the system might initially appear serene. A bright star, a dark giant world orbiting nearby, repeating transits, predictable motion. Only careful measurements reveal the deeper truth, the atmosphere escaping, the tidal stretching, the orbital decay, the ongoing destruction. Astronomy often works that way. The universe hides enormous violence beneath mathematical elegance. Black holes spin quietly, galaxies collide slowly, stars explode after millions of years of apparent stability, and hot Jupiters spiral inward patiently toward annihilation. One detail scientists find particularly useful about systems like WASP-12b is that they provide laboratories for studying tidal physics under extreme conditions. Tidal interactions occur everywhere in astronomy. Moons influence planets, planets influence stars, binary stars distort each other continuously. But most systems evolve too slowly for direct observation. Extreme hot Jupiters accelerate the process. They compress enormous astrophysical changes into timescales humans might actually detect. In some sense, these worlds allow astronomers to watch gravity working in near real time, and gravity here behaves almost mercilessly. The closer the planet gets, the stronger the distortion becomes. The stronger the distortion becomes, the more energy dissipates. The more energy dissipates, the faster orbital decay may proceed. A cosmic tightening spiral. And because the planet is already inflated by intense heating, it becomes even more vulnerable to tidal forces. The atmosphere extends farther outward, making atmospheric escape easier. The star effectively begins feeding on the planet while simultaneously dragging it inward. Destruction arrives from multiple directions at once. Yet despite all this, there's also something beautiful about the consistency of the physics involved. No chaos in the equations, no sudden magical failure. Gravity pulls exactly as expected. Heat transfers exactly as expected. Orbital mechanics proceed with relentless precision. Even catastrophe follows rules. That idea can feel strangely calming late at night. The universe may be dangerous, but it is deeply lawful. And perhaps that's why astronomers find systems like WASP-12b so mesmerizing. These worlds sit near the boundaries where familiar physics produces unfamiliar outcomes. A gas giant becomes stretched into an egg shape. Its atmosphere boils outward. Its orbit shrinks gradually. Its star consumes escaping material. A planet larger than Jupiter transformed into a temporary object by orbital proximity alone, all because gravity never stops working. Sometimes exoplanets make Earth feel astonishingly fortunate. Our orbit remains stable. Jupiter stays safely distant. No giant gas planet migrated inward to destabilize the inner solar system catastrophically. Earth experiences tides, certainly, but not enough to deform the entire planet visibly. The sun warms us without stripping away the atmosphere. Compared to hot Jupiters, the solar system feels remarkably civilized. That civilization may partly reflect luck, and luck in astronomy can matter enormously. One particularly sobering implication of planetary migration theories is that many young systems may experience violent rearrangements early in their history. Giant planets moving inward can scatter smaller worlds, destabilize orbits, or prevent habitable planets from forming entirely. A migrating hot Jupiter may transform an entire system permanently, which means worlds like WASP-12b are not merely strange isolated curiosities. They are clues about how planetary systems evolve broadly across the galaxy. Some worlds survive gravitational chaos, others become casualties of it. And some giant planets wander too close to the fire and spend their remaining existence spiraling slowly toward destruction. There's a strange poetry to that, even without using poetic language directly. Not emotional poetry exactly, more structural poetry. A giant world formed far out in cold darkness migrates inward across millions of years until eventually the very star that once merely illuminated it begins consuming it. A long orbital journey ending in heat and gravity. That thought feels strangely ancient somehow. Stars as cosmic recyclers. Worlds returning to stellar material. In a sense, planets originate from stars and eventually may return to them. The system closes. And perhaps that is partly why the story of WASP-12b feels so compelling. It is not simply a strange planet. It is a process caught midstream. A giant world in transition between existence and destruction. A planet already beginning to disappear. For most of human history, the night sky looked permanent. The stars returned to the same places. The planets wandered in predictable patterns. The moon changed shape reliably enough for calendars, harvests, navigation, and poetry all at once. Civilizations rose beneath the assumption that the heavens were stable, orderly, and eternal in ways Earth itself often was not. Then astronomy advanced far enough to reveal something slightly unsettling. Planetary systems are not permanent. They evolve, they migrate, they collide. Sometimes they even destroy themselves. And once people hear about a world like WASP-12b being stretched apart and slowly consumed by its star, the same question almost always appears eventually. Could something like this happen here? Could Earth ever spiral into the sun? Could Jupiter become a hot Jupiter? Could our solar system someday produce a planet being eaten alive by stellar gravity? The short answer is reassuring. No, nothing remotely similar is happening in our solar system right now. Earth is not secretly drifting toward the sun. Jupiter is not about to begin atmospheric evaporation, and the sun is not currently preparing to snack on any planets in the near future, which is probably comforting information to receive before bedtime. Still, the longer answer is more interesting because it reveals why the solar system turned out so comparatively calm in the first place. To understand that, it helps to start with distance. distance controls nearly everything in planetary systems. Temperature depends on distance, orbital speed depends on distance, tidal forces depend on distance, atmospheric stability depends on distance, and compared to WASP-12b, the planets in our solar system stay astonishingly far from the Sun. Mercury, the closest planet, orbits about 58 million kilometers away. Earth stays roughly 150 million kilometers distant. Jupiter remains even farther out at around 778 million kilometers. Meanwhile, WASP-12b orbits only around 3 million kilometers from its star. That number is so extreme it almost stops sounding meaningful after a while. The planet sits nearly 20 times closer to its star than Mercury does to the Sun. It lives inside a region of space our solar system essentially leaves empty. And that matters enormously, because tidal forces increase dramatically with proximity. Move twice as close to a massive object, and tidal effects do not merely double, they become vastly stronger. That is why Earth experiences relatively gentle ocean tides, while WASP-12b experiences planetary-scale distortion. The solar system simply lacks giant planets, orbiting dangerously close enough to the Sun for those effects to become catastrophic. Jupiter, despite being enormous, remains comfortably distant. Its atmosphere stays cold. Its structure remains stable. The Sun warms it gently rather than actively tearing it apart. In fact, Jupiter receives only about 4% of the sunlight Earth does. That alone shows how dramatically energy falls with distance. If you somehow moved Jupiter inward toward the Sun, things would become much stranger very quickly. Its atmosphere would heat dramatically, its cloud structures would change, tidal interactions would strengthen. At sufficiently close distances, Jupiter itself could potentially become a hot Jupiter. That idea sounds bizarre because humans instinctively think of planets as fixed where they belong. But exoplanets taught astronomers that planets migrate, and the solar system itself may once have looked very different. This is where things become especially fascinating. Modern planetary formation models suggest Jupiter probably moved inward somewhat early in solar system history, before migrating outward again. One influential idea, sometimes called the Grand Tack hypothesis, proposes that Jupiter drifted close to the Sun while interacting with the young solar system's gas disk. Then Saturn formed and altered the gravitational dynamics, reversing Jupiter's migration outward. If that model is correct, the solar system narrowly avoided becoming something much stranger, possibly much more dangerous. Because giant planets moving through young systems can destabilize smaller worlds dramatically. They scatter material, alter orbits, prevent stable terrestrial planets from forming properly. Some hot Jupiter systems may have once possessed Earth-like inner planets before migration disrupted everything. That realization changes how we think about Earth's existence. The solar system did not simply appear fully arranged and peaceful forever. It evolved, and perhaps evolved fortunately. Astronomy increasingly suggests that stable habitable worlds may depend partly on long sequences of gravitational luck, not magical luck, physical luck, orbital luck, timing luck. Jupiter may actually protect Earth in some ways precisely because it remained far away instead of plunging inward catastrophically. There's something humbling about that. Human civilization may partly exist because giant planets behaved themselves billions of years ago. Still, while nothing like WASP-12b threatens the solar system now, the Sun itself will eventually become far more dangerous. Stars evolve. That is another thing ancient humans could not easily know while staring at seemingly eternal constellations. The Sun burns hydrogen into helium deep within its core continuously. Over immense timescales, that process changes the star gradually. Billions of years from now, the Sun will exhaust core hydrogen and expand into a red giant. When that happens, the inner solar system changes dramatically. Mercury will almost certainly disappear entirely. Venus likely will too. Earth's fate is more complicated, but the planet will certainly become uninhabitable long before then. Oceans will evaporate, surface temperatures will soar, atmospheric chemistry will collapse. Whether Earth itself gets engulfed physically remains uncertain, though many models suggest the expanding sun may indeed consume it eventually. There is something strangely eerie about realizing Earth's ultimate fate may involve the sun after all. Not because Earth spirals inward like WASP-12b, but because stars eventually change enough to overtake nearby worlds. Of course, this process unfolds over billions of years, which is astronomically comforting. Humanity has more immediate concerns involving climate, geopolitics, and occasionally forgetting why we walked into rooms. Still, the broader point matters. Planetary systems are not permanent. Even stable ones evolve eventually. And exoplanets like WASP-12b help scientists understand those long-term processes more clearly. One reason hot Jupiters fascinate astronomers is because they accelerate astrophysical effects normally too slow to observe easily. Tidal interactions become stronger. Atmospheric escape becomes measurable. Orbital decay becomes detectable. It's rather like turning up the intensity knob on planetary physics until hidden mechanisms become visible. In calmer systems like ours, many of those same processes still exist, just far more gently. Earth loses tiny amounts of atmosphere to space continuously. The Moon slowly moves away from Earth because of tidal interactions. The Sun gradually brightens over time. Nothing in astronomy truly stands still. The difference lies mostly in scale and speed. For example, Earth's orbit is extremely stable over human timescales. The gravitational architecture of the solar system settled into long-lived configurations billions of years ago. Planetary migration largely ended after the chaotic early formation era. That stability matters enormously for life. Climate remains relatively predictable. Seasons persist. Liquid water survives. Earth's atmosphere stays gravitationally bound rather than boiling away into space. Compared to WASP-12b, Earth occupies a remarkably gentle environment. Exoplanets repeatedly remind us of this. Some worlds orbit so close to stars that years last days. Some are tidally locked permanently. Some lose atmosphere continuously. Some may rain molten material. And some giant planets spiral slowly toward destruction. Earth begins looking less ordinary and more carefully balanced by comparison. Another important difference involves the type of star itself. WASP-12 is somewhat larger and hotter than the Sun. More stellar radiation means harsher conditions at close orbital distances. Combined with the planet's extreme proximity, that produces the catastrophic environment astronomers observe. The Sun, meanwhile, remains relatively stable and moderate by stellar standards. That moderation helped life emerge. Stars matter enormously to planetary fate. Too active, and stellar radiation strips atmospheres away. Too massive, and stellar lifetimes become short. Too dim, and habitable regions shrink inward dangerously close. Again, the solar system appears surprisingly fortunate. Sometimes astronomy feels less like discovering that Earth is unimportant, and more like discovering how many conditions quietly cooperate to make Earth possible at all. Still, there are a few places within our solar system that hint faintly at some of the same physical processes seen in hot Jupiter systems. Take Jupiter's moon Io, for example. Io experiences extraordinary volcanic activity because Jupiter's gravity stretches and compresses it continuously through tidal interactions. The Moon flexes under gravitational stress, generating enormous internal heat. That process, tidal heating, resembles a much gentler cousin of what happens to WASP-12b. The difference is mostly intensity. Io remains solid. Its orbit stays stable. Jupiter does not actively consume it, but the same physical principles appear. Gravity stretches objects. Stretching creates friction. Friction creates heat. Astronomy loves repeating patterns across different scales. Another faint parallel involves atmospheric escape on Mars. Mars once possessed a thicker atmosphere long ago. Over billions of years, solar wind and weak gravity allowed much of that atmosphere to escape into space gradually. Again, the same underlying physics appears. Atmospheres can disappear, worlds can change dramatically. But on Mars, the process unfolded slowly and gently compared to the violent atmospheric loss occurring on WASP-12b. Exoplanets often work this way scientifically. They take familiar physical processes and push them to extremes. Tides become catastrophic. Heat becomes planetary-scale destruction. Atmospheric escape becomes measurable in real time. That's why astronomers study them so intensely. Extreme systems reveal hidden mechanisms more clearly. One especially intriguing question scientists still debate involves how common hot Jupiter death spirals really are across the galaxy. Some hot Jupiters may stabilize for long periods. Others may spiral inward rapidly. Some may already have vanished entirely, consumed by their stars long before humanity developed telescopes capable of noticing them. The galaxy could contain countless former planetary systems whose giant worlds already disappeared. In a sense, astronomy studies survivors. We observe systems caught during temporary moments of stability or transition. WASP-12b may represent one such moment. A giant world nearing destruction during the exact era humans became technologically capable of detecting it. That timing alone feels extraordinary. Human civilization occupies a vanishingly small slice of cosmic history. Yet somehow we exist during the period where a distant planet larger than Jupiter is actively evaporating into space in a measurable way. The universe did not need to make that observable, yet here we are, watching, measuring, learning. There's something strangely calming about that late at night. Humans remain tiny compared to the cosmos, certainly, but our curiosity reaches astonishing distances. We cannot physically visit WASP-12b. We almost certainly never will. Still, we know its atmosphere escapes. We know gravity stretches it. We know its orbit may decay. We know its sky never rests. All inferred from faint arriving light, crossing interstellar darkness. And perhaps the biggest lesson from all this is not really about destruction at all. It's about variation. The universe allows planetary systems to become wildly different from one another. Some remain stable and habitable, some grow chaotic. Some worlds freeze, some burn, some fall inward toward their stars. And among all those possibilities, Earth occupies an unusually gentle arrangement. A calm orbit, moderate sunlight, a breathable atmosphere, liquid oceans, a sky that cools at night. Compared to WASP-12b, our planet feels almost impossibly peaceful, which naturally leads to one question. What ultimately happens to a world once the spiral inward finally reaches its end? Nothing in the universe lasts forever. Not planets, not stars, not galaxies. Even the black holes that seem eternal eventually evaporate if you wait long enough. The cosmos is full of objects that appear stable only because human lifetimes are so short by comparison. We look at mountains and imagine permanence. We look at oceans and imagine continuity. We look at stars and instinctively assume they will always remain where they are. Astronomy gently corrects that assumption over and over again. Everything changes, everything evolves. And somewhere more than 1,400 light-years away, WASP-12b is already moving toward an ending written into its orbit long ago. Not tomorrow, not next century, but inevitably. That is the strange thing about the future of this planet. Scientists do not merely suspect it might eventually disappear. The physics of the system strongly suggest destruction is already underway. The only real question is how the final stages unfold. Will the atmosphere strip away gradually until only a dense core remains? Will tidal forces eventually tear the planet apart entirely? Will the world spiral directly into its star and vanish beneath the stellar surface? The universe has several possible endings prepared. None of them are particularly cheerful for the planet. Still, before we follow WASP-12b toward its final millions of years, it helps to pause and appreciate just how unusual this moment already is. Human civilization exists during the exact era where the planet remains observable but unstable. That timing is extraordinary. Billions of years ago, the planet likely had not yet migrated inward completely. Millions of years from now, it may no longer exist in recognizable form at all. But tonight, during this brief slice of cosmic history, the planet still circles its star every 26 hours while losing atmosphere into space. We happen to live during the chapter where the destruction is visible, and perhaps that is part of what makes the story feel so haunting. We are not looking at a completed event preserved in astronomical history. We are watching something mid-collapse, a world in transition, a giant planet caught between existence and disappearance. Astronomers estimate that WASP-12b may survive only a few million more years before tidal interactions and atmospheric escape fundamentally destroy it. Now, a few million years sounds wonderfully distant from a human perspective, because humans become emotionally calm around numbers large enough to inconvenience geology itself. But on cosmic scales, that is remarkably brief. Earth has existed for roughly 4.5 billion years. The sun will continue shining for billions more. Compared to ordinary planetary lifetimes, WASP-12b appears fragile and temporary, like a spark that wandered too close to a fire. One likely future involves continued orbital decay. The planet appears to be spiraling inward gradually due to tidal interactions with its star. Tiny shifts in transit timing suggest the orbital period may already be shrinking measurably. That means every orbit potentially brings the world slightly closer to danger. Closer means stronger gravitational distortion. Closer means more heating. Closer means faster atmospheric escape. The system behaves like a feedback loop that slowly intensifies over time. At first glance, orbital decay sounds dramatic, almost cinematic. But in reality, the process unfolds with enormous patience. The orbit tightens by tiny amounts. The atmosphere escapes gradually. Millions of years pass while the star and planet continue their gravitational dance. The universe rarely hurries destruction, it simply continues it. Eventually, though, the inward drift may push the planet beyond survival thresholds entirely. One possibility is complete atmospheric stripping. Gas giants like Jupiter and WASP-12b are made mostly of hydrogen and helium surrounding deeper layers enriched with heavier elements. If enough atmosphere escapes over time, the giant swollen envelope may gradually shrink away. The star would essentially peel the planet layer by layer. This idea fascinates astronomers because some ultra-short period rocky exoplanets discovered elsewhere may actually be the stripped cores of former gas giants. Imagine a planet beginning life larger than Jupiter and ending as a dense, surviving remnant after losing most of its atmosphere. Planetary evolution becomes almost metamorphic, worlds changing identity entirely across cosmic time. If WASP-12b follows that path, its final stages may reveal deeper planetary layers normally hidden beneath thick gas envelopes. Materials buried for billions of years could eventually become exposed. Of course, even those deeper layers would endure horrifying conditions near the star. Nothing about the system becomes gentle later. Still, the possibility is scientifically extraordinary because it means astronomers may eventually observe the transformation of one planetary class into another. Another possible ending is even more violent: tidal disruption. As the orbit shrinks further, the star's gravitational forces could eventually overwhelm the planet's ability to remain structurally intact. The atmosphere already extends dangerously close to the Roche lobe boundary, where stellar gravity dominates. Move slightly closer, and the imbalance worsens dramatically. The planet may begin losing mass faster and faster. the atmosphere stretches farther outward. Material streams toward the star more efficiently. At some stage, the entire structure could become catastrophically unstable, not a neat explosion, more like gravitational unraveling, a giant world pulled apart by the star piece by piece. The phrase tidal disruption sounds clinical, but the reality would be astonishing. Vast streams of planetary material spiraling into the star. Atmospheric layers stripped away continuously, orbital energy draining while the planet deforms under immense stress, a world transformed into stellar fuel. And then there is the most final possibility of all, direct engulfment. If the inward spiral continues long enough, the planet may eventually plunge into the star itself. That image feels almost mythological. A giant world disappearing beneath the surface of its own sun. But astronomers believe stars likely consume planets more often than humans once imagined. Some stars show unusual chemical abundances that may hint at past planetary engulfment events. Others brighten temporarily in ways suggesting fresh material recently fell inward. The galaxy may contain countless stars carrying traces of destroyed worlds inside them. Stars eating planets turns out not to be science fiction at all, just astrophysics. One especially eerie aspect of stellar engulfment is how ordinary it might appear from far away. There may be no galaxy-wide explosion, no dramatic shockwave. The star simply absorbs the planet. The atmosphere blends into stellar gas. The planet disappears into plasma and heat. Eventually, even the memory of its separate existence vanishes physically. That idea can feel strangely sad, even though planets themselves do not care. Humans naturally attach emotional weight to endings, especially slow ones. Perhaps because slow endings feel recognizable. WASP-12b does not die suddenly. It fades, it loses mass, it changes orbit, it stretches, it leaks atmosphere into surrounding space. The destruction unfolds gradually enough that astronomers must measure it through tiny variations in light and timing, a world dissolving almost quietly. There's something deeply haunting about that, especially at night. One fascinating scientific question involves how much of the planet's atmosphere the star has already consumed, because the process likely began long before humans evolved. The atmosphere may have been escaping for millions of years already. The planet we observe today could represent a diminished version of its former self. Perhaps it was once larger, more massive, less distorted. Hot Jupiters may spend long periods slowly eroding before finally reaching terminal stages visible to modern astronomy. That possibility changes how we think about planetary systems generally. Worlds are not fixed snapshots frozen forever. They evolve continuously. Planets migrate. Atmospheres escape. Stars brighten over time. Everything in the universe exists within processes. Even the solar system itself once looked dramatically different billions of years ago. And billions of years from now it will look different again. Astronomy constantly reminds us that stability is temporary, not fragile necessarily, but temporary. One especially interesting aspect of WASP-12b's future involves the star itself. As the planet spirals inward and transfers angular momentum through tidal interactions, the star may respond dynamically as well. The star and planet are not independent objects merely existing nearby. They influence each other continuously. The planet raises tides inside the star. The star raises tides inside the planet. Energy transfers between them. The system evolves together. This interconnectedness appears throughout astronomy. Nothing large exists entirely isolated. Gravity links objects across enormous distances. Moons shape planets. Planets influence stars. Galaxies distort one another. Even black holes alter surrounding space-time itself. WASP-12b simply demonstrates those interactions under extreme conditions, and because the conditions are so extreme, the physics becomes visible to human observation more easily than in calmer systems. In a sense, the planet's destruction teaches astronomers about gravity itself. Another curious detail about the future of hot Jupiters involves stellar aging. Over time, stars gradually evolve and brighten. As stars expand later in life, close planets face even harsher conditions. If WASP-12b somehow survived long enough for significant stellar evolution to begin, conditions would worsen dramatically. The star itself would eventually expand outward. The orbit would become even more dangerous, but realistically the planet may not survive long enough for those later stellar stages to matter much. Its current proximity already places it near destruction, and still it continues orbiting. That persistence is strangely remarkable. Despite everything working against it, the planet remains there tonight. A giant world larger than Jupiter still circling its star every 26 hours, still stretched by gravity, still losing atmosphere, still glowing under extreme heat, still existing, at least temporarily. Sometimes astronomy feels almost philosophical simply because the timescales involved are so enormous. Human lives pass quickly, civilizations rise and fall rapidly compared to planets and stars, yet even planets eventually disappear. WASP-12b reminds us of that clearly, not through sudden violence, through persistence, the same physical laws operating continuously until eventually the system changes entirely. Gravity never stops pulling, heat never stops transferring, stars never stop radiating energy, and over enough time those processes reshape everything. One of the quieter lessons of exoplanet science is that the universe allows extraordinary variety in planetary fate. Some worlds remain stable for billions of years, some freeze in darkness, some wander interstellar space alone, some burn beneath relentless stars, and some, like WASP-12b, spend their final era slowly unravelling while astronomers across the galaxy briefly notice. That brief noticing matters. Humanity exists during the period where telescopes are advanced enough to detect atmospheric escape, orbital decay, and tidal distortion from distant worlds. Earlier civilizations could only imagine strange planets philosophically. Future civilizations, if they exist, may know vastly more, but ours is the first era capable of seeing a giant exoplanet actively disappearing into its star. That achievement still feels astonishing, especially because the evidence arrives so quietly. A slight dimming of starlight, a subtle ultraviolet signature, tiny changes in transit timing. From those delicate signals, humans infer the fate of an entire world. The future of WASP-12b may ultimately end in destruction, but the process has already given humanity something remarkable in return: perspective. Extreme exoplanets often make Earth feel newly precious rather than insignificant. A stable orbit begins looking fortunate. Moderate sunlight begins feeling rare. A breathable atmosphere begins feeling extraordinary. Compared to WASP-12b, Earth lives in remarkable peace. No star strips our atmosphere away. No tidal forces stretch the entire planet visibly. No orbital decay drags us slowly inward toward destruction. The sky cools every evening. Clouds drift softly overhead. Oceans remain liquid instead of vaporized. The more astronomers discover about violent worlds elsewhere, the gentler our own planet begins to appear. And perhaps that is one of the quiet, emotional effects of astronomy people rarely mention. The universe contains so many hostile possibilities that Earth starts looking less ordinary and more miraculous by comparison. Still, WASP-12b continues its journey tonight regardless of human reflection. Another orbit, another year passing in just over a day, another stream of atmosphere escaping into space, another tiny step inward, and eventually, after enough millions of years, the planet's separate existence may end completely. The star will remain, the world will not, at least not in the form we recognize now. Yet even after the planet disappears, the story of WASP-12b will continue in another sense because its discovery permanently changed how humans understand planetary systems. Hot Jupiters stopped being impossible. Planetary migration became unavoidable. Atmospheric escape became observable. Orbital decay became measurable. And somewhere within all those scientific discoveries lies a strangely beautiful truth. The universe is not static. Worlds are not eternal. Everything moves, everything changes, everything leaves traces behind. Somewhere tonight, while Earth turns quietly beneath sleeping cities and dim apartment lights and distant passing cars, WASP-12b is still there, still orbiting, still overheating, still losing itself to the star beside it. Another year on that world has already passed while you've been listening. Perhaps several of them. An entire cycle around its star completed in less time than it takes most people to finish a quiet evening, wash dishes, or fall asleep on the couch with a blanket half slipping onto the floor. That alone feels strangely difficult to absorb. Time behaves differently across the universe. On Earth, a year carries emotional weight. We measure our lives with them. Birthdays, seasons, memories, entire eras of life quietly grouped into circles around the sun. One year can feel long when you're waiting for something difficult to end. Another can vanish almost instantly if life becomes busy enough. But on WASP-12b, years rush by continuously while the planet itself slowly disappears. A world racing through time while running out of it. And perhaps that is why this distant planet lingers in the imagination long after the science settles into place. Not because it is the largest exoplanet ever found, or the hottest, or the strangest in every category. The universe contains many bizarre worlds. But WASP-12b feels personal in an unusual way because it allows us to witness something the cosmos normally hides from human eyes. Change. Not sudden explosive change. Slow change. The kind that unfolds patiently, orbit after orbit, layer after layer. A planet larger than Jupiter gradually stretched, heated, and consumed by the same star it circles endlessly. There's something almost hypnotic about that image late at night. A dark, overheated world racing around its star every 26 hours while losing atmosphere into space. Winds screaming through skies hotter than lava. Gravity pulling harder each year. The orbit shrinking almost imperceptibly while the star quietly feeds on escaping gas. And all of it happening right now. Not metaphorically right now, literally. At this very moment, while Earth continues its comparatively gentle orbit around the Sun, that distant planet is still spiraling through another impossible year. Astronomy often makes the universe feel large, but sometimes it does something stranger. Sometimes it makes the universe feel active, not static scenery overhead, not decorative stars pinned against darkness, a living physical system where objects evolve continuously, whether humans notice or not. Stars burn fuel, galaxies rotate, black holes feed, planets migrate, and some worlds die slowly under relentless gravity. Before exoplanets were discovered, humans naturally assumed our solar system probably represented a fairly normal arrangement. Rocky planets inside, gas giants outside. Mostly calm orbits lasting billions of years. Then the galaxy opened itself to observation and revealed something far more chaotic. Some planets orbit two stars. Some wander through interstellar darkness alone. Some rain molten material. Some rotate so slowly that one side permanently faces their star. And some, like WASP-12b, drift too close to the fire and begin unravelling because of it. That realization changed astronomy profoundly. Planetary systems stopped feeling permanent. Worlds became dynamic things, temporary things sometimes. Even giant planets larger than Jupiter could end up unstable under the right conditions. Gravity, it turns out, is patient enough to dismantle almost anything eventually. Still, there is another side to these discoveries too. Extreme exoplanets often make Earth feel unexpectedly precious. The more astronomers learn about violent worlds elsewhere, the calmer our own planet begins to appear. Earth's atmosphere remains stable. The sun warms us without stripping our air away. The sky cools every evening. Oceans remain liquid instead of vaporized. No tidal forces stretch the entire planet visibly. No orbital decay drags us inward toward destruction. Compared to WASP-12b, Earth feels astonishingly gentle, and perhaps that is one of the quiet emotional gifts astronomy offers. It stretches perspective until ordinary things become extraordinary again. A breathable atmosphere becomes miraculous. A stable orbit becomes rare. Rain becomes beautiful. Even the simple existence of nighttime starts feeling fortunate once you've imagined a world trapped beneath permanent stellar exposure. On Earth, darkness arrives every evening almost like a kindness. WASP-12b never receives that relief. Its star never leaves the sky. Its atmosphere never stops moving. Its destruction never pauses, and still it continues orbiting. There's something strangely moving about persistence in astronomy. Objects continue obeying physical laws even during catastrophe. The universe rarely provides dramatic finales. Instead, it prefers continuation. Stars continue shining while consuming planets. Galaxies continue rotating while colliding. Worlds continue orbiting while falling apart. Everything keeps moving. And maybe that's partly why astronomy can feel calming despite the scale and violence involved. The cosmos behaves consistently. Gravity does not panic. Physics does not improvise. Even destruction follows rules patiently and precisely. WASP-12b is not being punished. It simply crossed into dangerous proximity long ago. Perhaps it formed far from its star before migrating inward through gravitational interactions. Perhaps for millions of years it orbited safely enough before tides and heat gradually intensified. Whatever its history, the planet eventually moved too close to stability's edge. Now the star pulls at it continuously. The atmosphere escapes, the orbit may shrink, and the future narrows slowly toward disappearance. One especially haunting aspect of all this is how invisible the process would seem without modern astronomy. If humans lived nearby and watched only casually, the system might appear calm. A bright star, a dark planet orbiting rapidly nearby. Only careful measurements reveal the deeper truth. Tiny shifts in transit timing, ultraviolet absorption from escaping gas, atmospheric signatures extending far beyond the planet itself. Evidence gathered photon by photon across years of observation. Humanity has become astonishingly good at noticing faint things. That may be one of civilization's quietest achievements. We evolved on one small rocky planet, throwing stones, building fires, worrying about weather, and occasionally eating suspicious berries despite generations of evidence suggesting caution. Now we detect dying worlds across interstellar space, and we do it using light that began travelling toward Earth centuries ago. The photons reaching telescopes tonight from WASP-12b left, while medieval kingdoms still existed on Earth. Long before modern science, long before electricity, long before anyone knew other planets existed at all. That light crossed 1,400 years of darkness before finally reaching human instruments capable of understanding it. There's something deeply beautiful about that journey. Astronomy often feels less like observing objects and more like listening carefully across impossible distances. And what WASP-12b tells us is strangely simple. Planets are not eternal. Stars reshape systems continuously. The universe is full of worlds living very different lives from ours, some calm, some violent, some temporary. And somewhere within all those possibilities, Earth occupies an unusually peaceful arrangement. That peace becomes easier to appreciate after spending time beside a dying planet. Perhaps that's why stories like this stay with people. They're not really only about exoplanets. They're also about scale, time, fragility, and perspective. They remind us how much can happen beyond the boundaries of ordinary experience. A year can last 26 hours. A sky can remain permanently lit. Gravity can stretch a world apart. A star can slowly consume its own planet. And still the laws of physics remain beautifully consistent throughout it all. Late at night, there is something almost meditative about that consistency. The universe may be strange beyond imagination, but it is not random. Everything connects, heat flows, gravity pulls, orbits evolve, stars shine, worlds change, and somewhere far beyond the quiet room you're in right now, WASP-12b continues its endless spiral beside the star that is slowly erasing it. Another orbit, another year, another stream of atmosphere escaping into space. The process will continue long after tonight ends for us here on Earth. Long after cities sleep, long after clouds drift across tomorrow's sky. Long after entire human generations pass, for millions more years that planet may continue circling while gradually unravelling, until eventually the orbit shrinks too far, the atmosphere thins too much, the tides grow too strong, and the world that astronomers once discovered through tiny flickers of starlight finally disappears into the star beside it. The star will remain, the planet will not. Yet in another sense, the planet has already accomplished something remarkable. It changed how humans understand the universe. Before worlds like WASP-12b were discovered, planetary systems looked simpler, more orderly, more familiar. Now we know better. The galaxy is full of strange architectures and dangerous worlds. And because of that knowledge, Earth feels newly extraordinary too. A calm blue planet orbiting at a safe distance beneath a sky that cools gently every evening. Not perfect, not eternal, but wonderfully peaceful compared to the furnace worlds scattered elsewhere among the stars. So tonight, as you settle back into the quieter gravity of the Earth again, perhaps keep one thought softly in mind. Somewhere out there, a giant planet is still circling too close to its star, losing itself little by little beneath a sky that never rests. And somehow, across 1,400 light-years of darkness, we learn to see it.